For millions of years, planet Earth was home to creatures that were far larger and stranger than most living animals today. Dense forests of giant plants spread across the land, insects reached sizes far beyond anything seen now, and huge animals moved across every environment. Survival during this time often meant avoiding powerful predators with massive teeth, while the skies were dominated by flying reptiles with wingspans greater than many modern birds. This era was not only about dinosaurs, it included many other remarkable forms of life that thrived in the land, oceans, and air long before humans appeared. How did species change over time? How did ecosystems adjust to new conditions, and how much more extreme Earth's past was compared to the present? Before we begin, tell us in the comments below where in the world you're watching from, and what time it is there for you now. Now, settle in as we uncover what Earth was like millions of years ago. Long before humans ever walked the Earth, the planet was filled with creatures so huge, strange, and powerful that they almost seemed like something from a dream. The land, the skies, and the oceans were once ruled by beings that today would appear impossible. They were far larger than most animals we know now, and their shapes, sizes, and ways of life were beyond anything we could find in the modern world. To understand this ancient time, we have to go back hundreds of millions of years to a world that looked and felt very different from the one we live in today. The Earth itself was younger then, still shifting, forming mountains, splitting continents, and building new seas. The climate in many parts of the world was warmer, and thick forests covered vast areas. Giant ferns and enormous conifers rose high above the ground. The air was richer in oxygen during some periods, which helped animals and plants grow to astonishing sizes. It was in these conditions that gigantic creatures appeared and thrived. Among the most famous of these ancient animals were the dinosaurs. These creatures lived for well over 160 million years, far longer than humans have existed. Some of them were small, no bigger than a chicken, but others were true titans of flesh and bone. The long-necked sauropods, for example, could reach lengths of more than 100 feet, their necks stretching high into the treetops to strip leaves from branches. Their massive bodies were supported by legs like tree trunks, and their sheer size made them almost untouchable by predators. These animals shaped the world around them, eating enormous amounts of vegetation and leaving behind deep footprints that hardened into stone and can still be seen today. The predators of that age were just as impressive. Creatures like the Tyrannosaurus Rex, whose name means king of the tyrant lizards, were apex hunters. This massive carnivore lived about 66 million years ago. It could grow over 40 feet in length and had teeth as long as a banana, sharp and serrated for tearing flesh. It was one of the most powerful land predators to ever exist. Its bite force was stronger than that of any animal alive today, strong enough to crush bone. The presence of such predators meant that the world of the dinosaurs was filled with constant tension, where every day was a fight for survival. But dinosaurs were only part of this larger picture. Before them, in even earlier times, the seas were ruled by other giants. Hundreds of millions of years ago, strange armoured fish swam through the oceans, some of them reaching lengths of 30 feet or more. One of the most fearsome of these was Dunkleosteus, a predator with jaws so strong it could slice through the toughest armour of other fish. It had no true teeth, but instead sharp, bony plates that acted like giant scissors. This was long before the rise of the dinosaurs, showing that Earth had been home to giants again and again across different ages. Insects too were once far larger than anything we see today. During the Carboniferous period, about 300 million years ago, dragonflies with wingspans wider than 2 feet flew through the air. These giant insects could grow so large because the air was richer in oxygen, allowing their bodies to take in enough to support such size. Imagine walking through a forest in that time, with enormous dragonflies buzzing overhead, giant millipedes longer than a person crawling through the undergrowth, and amphibians the size of crocodiles lurking near swamps. The ground would shake with life that was larger, stranger, and more powerful than anything we find in nature now. When it comes to reptiles of the prehistoric world, the oceans held their own titans as well. While dinosaurs ruled the land, enormous marine reptiles dominated the seas. The plesiosaurs, with their long necks and wide, flippered bodies, glided gracefully through the water. Some had short necks and massive jaws built for hunting other sea creatures, while others had incredibly long necks that gave them a unique advantage in reaching prey. Another group, the Mosasaurs, were fierce predators that looked like gigantic lizards adapted to life in the water. The largest could reach lengths of more than 50 feet, snapping up fish, turtles, and even other marine reptiles. The skies too were home to giants. Flying reptiles called pterosaurs appeared during the age of dinosaurs, and some grew to sizes that challenge our sense of possibility. Quetzalcoatlus, one of the largest known flying animals of all time, had a wingspan that stretched around 35 feet, as wide as a small plane. With a long pointed beak and hollow bones, it was light enough to fly yet large enough to tower over a human when standing on the ground. It is hard to imagine a world where such creatures could lift themselves into the air, but the balance of light bones, strong muscles, and favourable conditions made it possible. On land, not every prehistoric giant was a dinosaur. After the extinction of the dinosaurs around 66 million years ago, other enormous creatures took their place. Mammals began to grow larger and fill the empty roles left behind. In time, giant mammals appeared across the continents. The mammoths, with their long, curved tusks and thick, woolly coats, roamed the icy plains of the Ice Age. Some species stood taller than 10 feet at the shoulder, using their tusks to push away snow and reach buried plants. Alongside them were mastodons, relatives of elephants that lived in forests and fed on branches and leaves. There were also animals like the giant ground sloths, some of which stood over 20 feet tall when reaching up on their hind legs. They were slow-moving but powerful, tearing branches from trees and digging into the ground for roots. Saber-toothed cats, with their long, curved canine teeth, hunted across grasslands and forests, striking fear into the other animals of their time. These creatures were among the great mammals that shaped the post-dinosaur world. Even birds grew to incredible sizes. In South America, giant flightless birds called terrorbirds ruled as top predators for millions of years. Some stood over 10 feet tall, with huge hooked beaks that could crush the bones of their prey. They ran swiftly on strong legs, using their size and speed to overwhelm smaller animals. Across the seas, other enormous birds, like the extinct elephant bird of Madagascar, grew taller than 10 feet and laid eggs bigger than a human head. The pattern is clear. Throughout Earth's long history, nature has produced creatures that tested the limits of size and power. Each era, from the time of giant insects to the reign of the dinosaurs and the rise of huge mammals, had its own titans. These animals were shaped by the conditions of their time, by the climate, the availability of food, and the pressures of survival. The Earth we know today is quieter by comparison, its animals smaller, its landscapes less dominated by colossal forms. Yet the rocks, fossils, and bones left behind remind us of this earlier world, where every environment held beings beyond our imagination. Some of these giants were not only large but also strange in form. Take the Stegosaurus, for instance. This dinosaur had rows of tall plates rising from its back, each one as big as a human, and a tail tipped with sharp spikes. Though not as huge as the sauropods, it was still a remarkable sight, lumbering across the land with its unique armour. Then there was the Triceratops, with its massive bony frill and 3 sharp horns, one of the most recognisable dinosaurs. These creatures show that ancient giants were not just about size, but also about unusual appearances and adaptations. Other dinosaurs like the Spinosaurus challenged even the great Tyrannosaurus in size. The Spinosaurus could reach lengths of over 50 feet and may have weighed more than 20 tons. It had a long snout filled with sharp teeth, well suited for catching fish, and a sail-like structure on its back that made it stand out from all other dinosaurs. Scientists believe it spent much of its time in rivers and lakes, making it one of the few known swimming dinosaurs. This diversity of form shows how nature experimented with different ways of being a giant. One of the most fascinating parts of this story is how these giants disappeared. Many of them, like the dinosaurs, vanished in mass extinctions, events where huge numbers of species died out in a short time. The most famous of these was caused by a massive asteroid that struck Earth about 66 million years ago, ending the age of the dinosaurs. Others disappeared because of changes in climate, shifting continents, or the arrival of new predators. Each extinction reshaped the planet, clearing the way for new giants to rise. The story of life on Earth stretches across hundreds of millions of years, and through this vast timeline, there were long periods when the planet was home to creatures so large, so unusual, and so different from what we see today, that they almost seem like beings from another world. Scientists usually divide these immense stretches of time into three great eras: the Paleozoic, the Mesozoic, and the Cenozoic. Each one lasted for many millions of years, and each one gave rise to different giants that walked on land, swam in the oceans, or soared across the skies. By following the journey through these three immense chapters of Earth's history, one can see how life constantly changed, adapted, grew to enormous sizes, and sometimes vanished forever. The Paleozoic era was the earliest of these three, beginning more than 540 million years ago and lasting until about 250 million years ago. During this immense stretch of time, Earth saw the first rise of complex animal life, the spread of plants on land, and the growth of whole forests where there had once been only bare rock and shallow seas. In these ancient seas, creatures appeared that would look strange to us today. Among them were trilobites, armoured animals that crawled on the ocean floor, and giant sea scorpions known as eurypterids, some of which could grow longer than a man is tall. These giant predators ruled the waters for many millions of years, using their sharp claws to catch fish and other animals. Insects also began to appear on land during this era, and with the oxygen levels in the atmosphere higher than today, many of them grew to extraordinary sizes. Dragonflies with wingspans of more than 2 feet filled the air, and millipede-like creatures called Arthropleura could reach lengths of over 6 feet, making them some of the largest land invertebrates in history. In the Carboniferous period, which was part of the Paleozoic era, vast swampy forests stretched across the planet, filled with towering club mosses and giant horsetails that reached heights of over 100 feet. These dense forests not only provided a home for massive insects and amphibians, but also gave rise to the coal deposits that people mine today. As the Paleozoic moved into its later stages, vertebrates, animals with backbones, began to grow larger and more dominant. Amphibians, which lived both in water and on land, grew to enormous sizes, some reaching lengths of over 20 feet. Early reptiles also appeared, adapting to life fully on land, setting the stage for the creatures that would follow in later eras. But the Paleozoic era came to a devastating end with the greatest mass extinction in Earth's history, often called the Permian extinction, around 250 million years ago. During this event, nearly 90% of species in the oceans and a huge number on land were wiped out. This catastrophe cleared the way for new forms of life to rise and dominate in the next great era. The Mesozoic era, which followed, stretched from about 250 million years ago to around 66 million years ago. It is often called the Age of Reptiles, and it was during this time that some of the most famous and massive creatures to ever live on Earth came into being. In the oceans, gigantic reptiles such as Ichthyosaurs, plesiosaurs and mosasaurs hunted fish and other marine life. Some Ichthyosaurs reached lengths of over 70 feet, while the long-necked plesiosaurs stretched out with their paddle-like limbs, cruising through the waters in search of prey. On land, the dinosaurs became the true rulers. They appeared early in the Mesozoic and eventually grew into a huge variety of shapes and sizes, from small bird-like hunters to the towering plant-eating sauropods that could stretch over 100 feet from head to tail. Creatures like Brachiosaurus, Diplodocus and Argentinosaurus are among the largest animals ever to walk on land. Their massive bodies, long necks, and towering heights allowed them to reach leaves from the tops of trees that no other animal could touch. But it was not only the plant-eating giants that roamed the land. Predatory dinosaurs such as Allosaurus and later Tyrannosaurus Rex stood at the top of the food chain, their enormous skulls filled with sharp teeth designed for crushing bones and tearing flesh. Other predators, such as Spinosaurus, grew even larger, with long, crocodile-like snouts and sails along their backs. Flying reptiles also filled the skies during the Mesozoic era. These were the Pterosaurs, some of which grew to wingspans longer than a small airplane such as Quetzalcoatlus, which may have had wings stretching more than 30 feet across. Insects during this time were smaller than those of the Paleozoic, but dinosaurs themselves gave rise to new evolutionary paths that would eventually lead to the first true birds. The lush world of the Mesozoic was filled with ferns, cycads, and conifers, creating landscapes that supported these immense reptiles for over 180 million years. The Mesozoic era, however, also came to a violent end. About 66 million years ago, a massive asteroid struck Earth near the region that is now the Yucatan Peninsula in Mexico. The impact caused global fires, blocked sunlight with dust and debris, and led to dramatic climate changes. Almost all the large dinosaurs and many other giant reptiles disappeared during this mass extinction event. Yet life continued, and in the era that followed, new giants rose to take their place. The Cenozoic era, beginning 66 million years ago and lasting to the present day, is often called the Age of Mammals. With the dinosaurs gone, mammals, which had been small and relatively unnoticed during the Mesozoic, suddenly expanded into a wide variety of forms and sizes. Some of these mammals became the giants of their time. Early in the Cenozoic, enormous flightless birds such as the terror of South America grew up to 10 feet tall and used their strong beaks to hunt smaller animals. In the oceans, whales began to evolve, eventually becoming the largest creatures ever known. Blue whales, which still swim in the seas today, can grow longer than 100 feet and weigh more than 150 tons, making them heavier than even the largest dinosaurs. On land, the Cenozoic produced massive mammals such as the woolly mammoth, which stood taller than today's elephants and carried enormous curved tusks, and the mastodons, which were slightly smaller but still impressive in size. There were also giant ground sloths, some as large as elephants, that roamed the forests of the Americas, using their huge claws to pull down branches. Rhinoceros-like animals such as Paraceratherium became the largest land mammals ever, standing over 16 feet tall at the shoulder and weighing many tons. Predators grew large as well, with saber-toothed cats such as Smilodon developing long sharp canine teeth that could reach over 7 inches in length. Bears, wolves and other carnivores also reached impressive sizes during this time. The Cenozoic era also saw the spread of humans, who appeared much later in the timeline, only a few million years ago. While humans themselves were not giants compared to some of these creatures, they eventually became one of the most influential forces in the natural world, contributing to the extinction of many of the Cenozoic giants. The mammoths, giant sloths, and saber-toothed cats all disappeared within the last tens of thousands of years, leaving behind only bones, fossils, and the stories written into the earth itself. Yet even today, the age of giants is not entirely gone, because creatures such as elephants and whales continue to represent the incredible scale that life on Earth can reach. Looking back at these 3 enormous eras, Paleozoic, Mesozoic, and Cenozoic, it becomes clear that life has always had the potential to grow into forms that are immense and awe-inspiring. Each era was shaped by the climate, the atmosphere, and the opportunities of its time. In the Paleozoic, the rise of forests and high oxygen levels allowed insects and amphibians to grow to massive sizes. In the Mesozoic, the dominance of reptiles produced the legendary dinosaurs and giant marine reptiles, along with flying creatures that stretched across the skies. In the Cenozoic, the fall of the dinosaurs opened the way for mammals and birds to expand, leading to some of the largest creatures the planet has ever seen. Across hundreds of millions of years, Earth has always been a world where giants rise, thrive, and sometimes vanish, only to be replaced by new forms that continue the endless story of life. Primeval forests and swamps were once the most striking features of the ancient Earth, shaping entire landscapes with their rich greenery and strange forms of life. Long before humans appeared, long before cities and machines, the world was covered with forests so thick and swamps so wide that they seemed endless. These places were not just wild and full of vegetation, they were also the settings in which giant creatures thrived. The trees, ferns, mosses, and towering plants created a kind of natural home where enormous insects, reptiles, amphibians, and later even dinosaurs lived, hunted, and hid. The air was heavy and humid, and the soil was always damp, feeding the growth of plants that reached incredible sizes. This abundance of food and shelter gave life the chance to grow larger than in many other times in Earth's history. Millions of years ago, during the great ages that stretched from the Paleozoic to the Mesozoic and beyond, forests and swamps created an environment that was unlike anything we know today. The air contained much more oxygen than it does now, and this made it possible for insects and other animals to grow far larger than their modern relatives. Giant dragonflies with wings as wide as the length of a human arm drifted through the air above these forests, hunting smaller creatures and feeding on anything they could catch. Enormous millipedes, longer than a grown person is tall, crawled along the damp forest floor. Amphibians with wide jaws rested in swampy waters, waiting to snap at passing prey. The dense vegetation gave all of them shelter and made the ground beneath their feet soft and wet. which was perfect for the survival of creatures that preferred both water and land. These forests were often filled with strange trees, many of which are no longer alive today. Huge club mosses, some as tall as modern buildings of several stories, grew in dense stands. Their bark-like surfaces and towering height made them look like forests of pillars. Alongside them grew tree-sized horsetails and giant ferns with leaves stretching out like massive umbrellas. The canopy they created blocked much of the sunlight, leaving the forest floor dim and shadowy. In these dim places, fungi and mosses thrived, and pools of still water collected in hollows, giving rise to rich swamps where even more creatures lived. It was in such primeval swamps that many of the world's great coal beds were formed. Over millions of years, the remains of fallen trees, ferns, and plants sank into the muddy ground, layering upon one another. Compressed by the weight of time and earth, they transformed into thick beds of coal, which humans would one day dig up and burn for energy. But in those ancient times, no one was digging. The coal beds were simply the result of endless cycles of growth, death, and decay in the primeval swamps. The climate of this world was warm and wet, much warmer than what most people experience today. Tropical conditions stretched far into regions that are now cold or temperate. The humidity in the air, the abundance of rainfall, and the lack of freezing winters allowed plants to grow throughout the year without pause. Because the plants never stopped growing, they provided an endless supply of food for herbivorous creatures. These plant eaters in turn provided food for predators, creating ecosystems that supported enormous sizes. A giant creature requires a great deal of food, and in the primeval forests and swamps there was no shortage of it. During the Carboniferous period, which began more than 350 million years ago, these lush forests were at their peak. It was during this time that the air contained much higher levels of oxygen, sometimes more than 1/3 of the atmosphere. This allowed even simple arthropods like insects and spiders to grow into giants. A dragonfly called Megalodon, with a wingspan of more than 2 feet, ruled the skies of these forests. On the ground, Arthropleura, an enormous millipede-like creature that could grow longer than 10 feet, moved slowly through the undergrowth, feeding on rotting plants. Amphibians of many shapes and sizes, some as small as modern frogs and others as long as crocodiles, hunted along the water's edge. The forests and swamps gave them hiding places, food, and constant access to water, making these landscapes ideal for their survival. Later, as millions of years passed, the world's forests changed. The great swamp forests of the Carboniferous gave way to different types of vegetation in the Permian period. The giant club mosses and horsetails began to disappear, replaced by seed plants that were better adapted to drier conditions. But in many parts of the world, swamps and dense forests still remained, and these continued to shelter large creatures. In these times, the ancestors of reptiles grew in number and variety, preparing the way for the dinosaurs of the next great era. When the Mesozoic era arrived, starting more than 250 million years ago, forests and swamps again provided the backdrop for giants. Conifer trees became widespread, creating forests of tall, straight trunks with needle-like leaves. Ferns still covered the ground, and cycads with thick trunks and crown-like leaves added variety to the landscape. In many regions, swamps with rich vegetation still spread across lowlands, rivers, and coastlines. These habitats became the homes of the first dinosaurs, and as the era unfolded, they supported some of the largest animals to ever walk the earth. The great sauropods, long-necked plant eaters that could reach lengths of more than 100 feet, relied on these forests for their survival. They fed on the leaves of tall trees and stripped entire branches with their peg-like teeth. The forests gave them both food and protection, as their enormous bodies could blend into the dense trunks and shadows. Swampy regions were especially important because they allowed the growth of lush plants year-round. Dinosaurs such as Diplodocus, Brachiosaurus, and Apatosaurus wandered in herds through these landscapes, while predators like Allosaurus and later Tyrannosaurus waited in ambush at the edges of forests and wetlands. Not only did the forests and swamps feed these giants, but they also gave birth to new forms of life. Birds, which evolved from small feathered dinosaurs, first spread their wings in forested landscapes, darting between trees in search of insects and small reptiles. Crocodiles, which still exist today, lurked in the swamps and rivers, just as their ancestors had done millions of years earlier. Turtles, frogs, and many other animals found the primeval swamps a perfect place to survive, for the mixture of land and water created endless opportunities for life. Even in the Cenozoic era, after the age of dinosaurs ended about 66 million years ago, primeval forests and swamps remained important. They became the homes of new giants such as the enormous mammals that dominated the Earth for millions of years. Mammoths, mastodons, giant ground sloths, and huge rhinoceros-like creatures called Ichthyosaurs thrived in forests where trees and plants were abundant. Swamps and wetlands provided water and shelter for these beasts, just as they had for the reptiles of earlier times. Although the Earth's climate had cooled compared to the Carboniferous and Mesozoic ages, vast stretches of tropical forest still existed in many regions, continuing the ancient role of feeding and sheltering giant animals. In these forests, the diversity of plants was astonishing. There were palms, figs, and flowering trees spreading their branches wide, while thick vines twisted from trunk to trunk, creating a green maze. In swampy areas, reeds, grasses, and water plants thrived, feeding countless herds of animals. Predators, whether big cats like saber-toothed tigers or giant flightless birds, hid in the shadows and hunted those who came to drink from swampy pools. The cycle of life in these places was as old as the Earth itself. Plants provided food, herbivores ate the plants, carnivores hunted the herbivores, and all of them depended on the lush, primeval environments of forests and swamps. If one were to walk through one of these primeval forests, the experience would be unlike walking through any forest today. The air would feel heavier, full of moisture and rich with the scent of plants. The ground would be soft and uneven, covered with moss, rotting wood, and pools of water. Strange sounds would echo through the trees, from the buzzing of insects larger than a person's hand to the croaks and bellows of amphibians bigger than modern crocodiles. Overhead, giant leaves would block the sun, casting everything in a green glow. In the distance, the splash of a huge reptile or amphibian entering the water would remind any listener of the hidden life that filled every corner of the swamps. These landscapes were not only homes but also engines of change. The forests and swamps of the Carboniferous helped create much of the oxygen that filled the air and allowed animal life to thrive. They locked away vast amounts of carbon in the form of coal, shaping the very balance of Earth's atmosphere. The forests of the Mesozoic gave rise to new groups of animals, from birds to mammals, by offering endless niches to fill. And even in the Cenozoic, the forests and swamps provided the environment in which early humans evolved, supplying them with food, water, and shelter just as they had for all the giants before. The primeval forests and swamps, stretching across millions upon millions of years, were the stage upon which the drama of giant life unfolded. Every leaf, every tree, every pool of water contributed to an environment where creatures could grow to enormous sizes. The sheer abundance of food made it possible. The shelter provided by thick vegetation kept animals safe from the burning sun and gave them places to hide from predators. The constant warmth and wetness of the climate ensured that life continued without pause, never slowed by winter or drought. In those days, the earth itself seemed to breathe with life. The forests and swamps were like endless gardens, but wild, untamed, and full of creatures that today would look like monsters. Their legacy is still with us, in the coal we burn, in the fossils we uncover, and in the ecosystems of forests and wetlands that survive today. Though the primeval world is gone, the story of its lush forests and swamps remains one of the most extraordinary chapters in the history of life on Earth. Earth was not ruled only by giant reptiles or huge mammals. There was also a time when insects themselves grew to astonishing sizes, reaching lengths and wingspans that seem unbelievable when compared to the insects we see today. The air, the climate, and the conditions of the planet allowed them to grow far beyond what modern insects could ever reach. Among these giants were dragonflies with wings as wide as a hawk's, and millipedes so long they stretched farther than the length of a car. These enormous creatures filled the forests and swamps of the ancient world, making the ground, trees, and skies buzz and crawl with life that would seem terrifying to us if we could see it now. One of the most famous of these insects was a dragonfly-like predator called Megalodon. This giant insect lived more than 300 million years ago during the Carboniferous period, a time when the world was covered with dense forests, vast wetlands, and huge swamps. Megalodon had wings that stretched wider than 70 centimeters across, which is wider than the outstretched arms of a small child, and in many cases its wingspan was almost as broad as that of some birds we know today, such as hawks. If you were to stand in one of those primeval forests, you would not only see towering trees and thick ferns, but you would also see these giant dragonflies swooping above. If you were to stand in one of those primeval forests, you would not only see towering trees and thick ferns, but you would also see these giant dragonflies swooping above, hunting other insects and even small amphibians with great speed. Their enormous wings, with their delicate patterns of veins, shimmered in the sunlight as they darted through the air, searching for prey. The sound of their wings beating would not have been the light, almost silent flutter we know from modern dragonflies. Instead, the air would have been filled with a deeper, louder hum, like the sound of a bird passing overhead. Another incredible insect of this time was the millipede-like creature known as Arthropleura. This was not the kind of small, many-legged bug that hides under rocks today. Arthropleura was a massive invertebrate, stretching over 2.5 meters long, which is longer than an adult human lying flat on the ground, and in some cases it may have reached nearly 3 meters. To understand its scale better, it was longer than many cars are wide, and taller than a person's knee when crawling along the forest floor. It had a hard, segmented body made up of armoured plates, and each section carried pairs of legs that allowed it to crawl steadily across the swampy earth. Its many legs moved in a wave-like rhythm as it pushed through thick layers of fallen leaves and vegetation, feeding mostly on rotting plants. The sheer size of Arthropleura made it the largest known invertebrate to ever walk the earth, a title it still holds in the fossil record. If you walked through the forests of the Carboniferous period, you would have had to step carefully, because these huge millipedes left tracks on the ground as they moved, trails so large and clear that some of them have been preserved in stone for millions of years. The reason insects like Meganeura and Arthropleura could grow so big has much to do with the atmosphere of the Earth at that time. During the Carboniferous period, the air contained far more oxygen than it does today, nearly a third of the atmosphere compared to the 1/5 we breathe now. Insects do not breathe with lungs like humans or animals, but instead draw oxygen directly into their bodies through tiny tubes called spiracles. The higher oxygen levels of the time allowed them to take in more oxygen than modern insects can, which supported the growth of their massive bodies. Today, insects are limited in size because their breathing system cannot carry enough oxygen to feed larger bodies. But in the ancient world, the air was rich enough to fuel giants. This, combined with the warm and humid climate and the dense vegetation that provided food and shelter, created the perfect environment for insects to reach sizes that seem monstrous to us today. In those lush primeval forests, the buzzing of insects would not have been from tiny creatures like bees or flies, but from larger, more imposing beings. Imagine standing in the shadow of giant trees, their trunks stretching upward like pillars, while leaves bigger than your head rustled above. Around you, insects the size of birds darted from branch to branch, while huge millipedes crawled over fallen logs. There were also scorpions, not the small ones we fear in deserts today, but enormous species that grew to almost a meter in length, creeping along the forest floor with their large pincers ready. There were also giant cockroaches and grasshopper-like insects that filled the undergrowth. The world was alive with motion, a continuous background of legs crawling, wings buzzing and jaws clicking. The giant dragonflies, especially Meganeura, were some of the top predators of their world. They did not feed on plants like many other insects, but were carnivorous hunters. They preyed on smaller insects and even small vertebrates. Their sharp jaws were perfect for seizing struggling prey, and their large eyes gave them excellent vision to spot movement. These creatures were the masters of the air in their time, unmatched in their speed and agility. To the creatures of the swamp, the sudden shadow of Meganeura's wings could mean death, just as the shadow of a hawk does for small animals today. Fossils show that their bodies were strong and well adapted for their role, with long, slender abdomens and powerful muscles that powered their wings. Arthropleura, on the other hand, was a creature of the ground, shaping the environment in its own way. As it crawled over the forest floor, it fed on dead plants and may have even grazed on low vegetation, helping recycle nutrients back into the soil. Its massive body would have disturbed the leaf litter, and its many legs left long tracks in the mud. In some places, fossilized tracks of Arthropleura have been found so wide and distinct that scientists could estimate its size without finding a full-body fossil. The fact that such an animal even existed shows how different Earth's past was compared to today. No modern invertebrate, whether insect, spider or millipede, comes close to its size. The biggest living millipedes today are only about 30 centimeters long, less than 1/8 the length of Arthropleura. The variety of oversized insects during the Carboniferous and Permian periods was not limited to just dragonflies and millipedes. Fossil records show that giant relatives of cockroaches, crickets and beetles also roamed the ancient landscapes. Some of these reached lengths of 10 to 15 centimeters or more, sizes that would seem alarming if we saw them in our homes today. There were also giant water scorpions, known as Eurypterids, which could grow up to 2.5 meters long. Although not insects but relatives of scorpions and spiders, these creatures ruled rivers and swamps, preying on fish and smaller animals. The world was filled with giants not only on land but also in the water and air, and insects were a major part of that dominance. The dominance of giant insects, however, was not permanent. As the Carboniferous period ended and the Permian period began, the Earth's climate changed. Oxygen levels in the atmosphere began to drop closer to modern levels, and the environment became less favourable for enormous insects. At the same time, new predators appeared. The earliest reptiles and amphibians were becoming more widespread and better adapted to hunting, which put pressure on the giant insects. Birds had not yet evolved, but flying reptiles and other vertebrate predators eventually filled the skies in later periods, reducing the role of giant insects as top hunters. By the time dinosaurs began to dominate the Earth in the Mesozoic era, insects had already shrunk closer to their modern sizes, no longer reaching the massive proportions of their ancestors. Even though giant insects are no longer with us, their fossils and preserved tracks tell us much about how life on Earth adapts to different environments. The discovery of Meganeura fossils in France in the late 19th century stunned scientists, who at first could hardly believe an insect could be so large. The wings, with their clear venation patterns, preserved perfectly in stone, gave direct proof of their existence. Arthropleura tracks found in parts of Europe and North America are equally stunning, showing the size and spread of these ancient millipedes. In some fossil beds, entire layers of rock are filled with impressions left behind by the many-legged movement of Arthropleura and its kind. The thought of insects so big raises many questions about how they behaved. For example, how would Meganeura's flight compare to that of modern dragonflies? Studies suggest that despite their size, they were still excellent flyers, able to hover, glide, and dart quickly. Their bodies were light enough, and the high oxygen levels gave them the energy they needed. Arthropleura, though huge, was likely a slow-moving grazer, not a predator. Its mouthparts suggest it fed on plants rather than hunting, though its sheer size meant that few animals would dare attack it. In fact, with its hard armour and giant size, Arthropleura may have had no natural predators for much of its existence. The giant insects of the past also show how fragile ecosystems can be. Their great size depended on a balance of oxygen, climate, and plant growth that lasted for millions of years. When that balance shifted, their size became impossible to maintain. Today's insects are far smaller, but they are far more adaptable, surviving in deserts, rainforests, mountaintops, and even cities. The age of insect giants may be long gone, but it remains one of the most fascinating chapters in Earth's history. The thought of walking in those ancient forests brings many vivid details to mind. The air would have been heavy and damp, filled with the rich smell of rotting plants. Strange calls from amphibians would echo through the trees, and above it all, giant dragonflies would dart like living spears of light, while below, massive millipedes pushed slowly through the ferns. Every corner of the world was alive, buzzing, creeping, and crawling with creatures far beyond what we know today. The reign of giant amphibians was one of the most unusual and fascinating chapters in the long story of life on Earth. During this time, the planet was warm, wet, and covered in endless forests and swamps that stretched across vast regions. These environments created the perfect conditions for strange and enormous amphibians to thrive, many of which looked very different from the small frogs and salamanders we know today. Among the most extraordinary of these creatures was Prionosuchus, a swamp-dwelling predator that grew to crocodile-like proportions, making it one of the largest amphibians to ever walk the Earth. To truly understand how such animals could exist, it is important to imagine what Earth looked like during this period. This was not the modern world, with its cities, farms, and carefully divided landscapes. Instead, giant ferns, towering horsetails, and trees with strange bark patterns filled the land. Swamps stretched for hundreds of miles, their surfaces covered with thick layers of moss, floating plants, and tangled roots. The air was heavy and damp, filled with the sounds of insects buzzing and the calls of creatures that lived both on land and in water. It was in these watery realms that amphibians found their greatest success. Unlike today, where amphibians are often small and fragile, back then they were powerful, large-bodied animals that often ruled their environments as top predators. Prionosuchus was a perfect example of this dominance. This gigantic amphibian, which lived in what is now South America roughly 270 million years ago, could grow longer than many modern crocodiles, reaching an estimated length of more than 30 feet. Its skull alone stretched several feet, lined with sharp, conical teeth that were perfectly adapted for gripping slippery prey like fish. The body of Prionosuchus was long and muscular, with short but strong limbs, a flattened tail, and skin that likely felt rough and moist. It probably spent most of its time in the water, hiding among the weeds or waiting in the shallows for unsuspecting prey to pass by. When something moved close enough, it would strike with incredible speed, snapping its jaws shut with force and dragging its victim beneath the surface. The lifestyle of Prionosuchus was very similar to that of modern crocodiles, but it was not a reptile. It belonged to a very different lineage of animals. Amphibians were among the first creatures to make the leap from water to land, and by this stage in Earth's history they had already developed into a wide variety of forms. Some were small, insect-eating species, while others became massive, semi-aquatic hunters like Prionosuchus. This variety shows how flexible amphibians were and how well they could adapt to different environments. In the warm and swampy lands of the Permian period, this adaptability allowed them to thrive and spread widely. Life in the swamps of the Permian was full of both opportunities and dangers. The wetlands teemed with fish of many different sizes, and these were the main source of food for Prionosuchus. Smaller amphibians and perhaps even some early reptiles may also have fallen victim to its ambushes. The swamps were also alive with enormous insects, some of which had wingspans as wide as a bird's. These insects may not have been prey for a predator as large as Prionosuchus, but their presence shows how abundant life was during this age. Amphibians like Prionosuchus thrived in this richness, dominating the waters in the same way that large carnivores dominate savannas and forests today. Despite its size and strength, Prionosuchus was not completely safe. There were other large predators that competed for space and food. Some of the early reptiles were already becoming more advanced, and they too hunted in the swamps. While Prionosuchus had a clear advantage in size, reptiles were slowly evolving traits that would help them dominate in the future. These early reptiles were less tied to water, their eggs could survive on dry land, and their bodies were better suited to withstand drier conditions. This meant that while amphibians like Prionosuchus thrived in the swamps, they were limited to these watery environments, while reptiles could begin spreading into new and more varied landscapes. Still, during its reign, Prionosuchus was one of the top animals of its world. Its body design was highly effective for hunting, and its size alone would have discouraged many smaller predators from challenging it. By lurking in water and striking at prey, it made full use of its environment. The structure of its teeth suggests it was a specialist in grabbing and holding slippery creatures, meaning that fish were probably its main diet. However, its enormous size also suggests that it could overpower and consume almost anything smaller than itself that came too close, including other amphibians. The discovery of Prionosuchus fossils in Brazil gave scientists an extraordinary glimpse into the diversity of amphibians in the distant past. These fossils showed that amphibians were once capable of reaching sizes that are almost impossible to imagine today. A modern frog can fit in the palm of your hand, while the largest living amphibian, the Chinese giant salamander, can grow to about 6 feet long. Compared to this, a creature more than 30 feet long is staggering, showing how different the conditions of ancient Earth were. The rich oxygen levels of the atmosphere, the warm climate, and the abundance of watery habitats all played roles in allowing such giants to exist. Amphibians of the Permian period came in many other shapes and sizes too. Some had bodies shaped like broad, flat discs that allowed them to stay hidden at the bottom of pools. Others had long, eel-like forms that helped them slip easily through weeds and mud. Some were heavily built, with wide heads and strong jaws designed for crushing. Together, they made up an entire community of amphibians that occupied different ecological roles, from small insect eaters to enormous predators like Prionosuchus. This shows how important amphibians were during this time. not just as side characters in the story of evolution, but as central figures in their ecosystems. The life of an amphibian in these swampy lands was not only about hunting. Reproduction played a major role in their survival. Unlike reptiles, which developed hard-shelled eggs that could survive in dry places, amphibians still relied on water for their eggs to hatch. This meant that their lives were tied to rivers, lakes, and swamps. For Prionosuchus, the shallow waters of the wetlands would have been the ideal place to lay eggs. Tadpoles, much like those of frogs today, would have hatched from these eggs and lived their early lives in the water, feeding on tiny plants and microorganisms before slowly developing into adults. This life cycle tied them firmly to aquatic environments, making swamps both their hunting grounds and their nurseries. The physical appearance of Prionosuchus must have been both terrifying and impressive. Its head was long and narrow, resembling the skull of a modern gharial, a type of crocodile with a slender snout. Its teeth were sharp and pointed, perfect for spearing fish. Its eyes were positioned on top of its head, which suggests it spent much of its time partly submerged, waiting to spot prey above the surface. Its long, muscular body, combined with a strong tail, allowed it to move quickly through water, lunging forward with surprising speed for such a massive creature. On land, it would have been slower, dragging its body with short legs, but in the water, it was a master hunter. The existence of Prionosuchus also tells us much about how animals adapt to their environments. Amphibians like this did not need to chase prey across long distances or run swiftly on land. Instead, they specialized in stealth, patience, and sudden attacks. This style of hunting was made possible by the swamps, where murky waters and dense vegetation provided plenty of cover. In such conditions, being able to remain still and wait for prey was far more effective than being able to run. This is why amphibians of this size were so successful in swampy habitats. As the Permian period continued, however, the world began to change. Shifts in climate and environment slowly made life harder for giant amphibians. As dry conditions spread into areas that were once covered in swamps, reptiles gained an advantage. They were better suited to survive in these harsher environments, while amphibians remained tied to water. Over time, this difference would shape the future of life on Earth, leading to the rise of reptiles and eventually the dominance of dinosaurs. But during their own time, giant amphibians were a powerful and impressive group, and Prionosuchus stood as one of their most extraordinary members. It is worth thinking about what it would have been like to stand near one of these creatures. The sight of a 30-foot-long amphibian resting in the shallows, with only its eyes and nostrils showing above the surface, would have been unforgettable. The sudden splash of water as it lunged at prey would have startled any observer. Its sheer size would have made it one of the most feared animals in the swamps, and yet it was part of a world where many creatures were growing to astonishing sizes. Dinosaurs were among the most remarkable living creatures that ever walked the earth. They were not just large reptiles, but a vast group of animals that changed over millions of years, creating a world filled with many shapes and sizes. They ruled the land for an incredibly long stretch of time, lasting for well over 160 million years, from the late part of the Triassic period, which began more than 200 million years ago, until the end of the Cretaceous period, around 66 million years ago. During this enormous span of time, dinosaurs spread to almost every corner of the world. They were not only survivors, but also innovators, in the sense that their bodies and ways of life kept changing to fit different environments. Among the greatest of these were the Sauropods, the Theropods, and the armored dinosaurs, each group shaping the land in its own way and leaving behind bones and fossils that still capture attention today. The Sauropods were perhaps the most astonishing of all dinosaurs in terms of size. They grew to lengths that no land animal has ever matched. Some sauropods stretched over 100 feet from head to tail and weighed as much as 50 to 100 tons, which is equal to the weight of several dozen elephants. These giants walked on 4 thick legs, almost like living columns, and their bodies were built like massive bridges that balanced long necks and equally long tails. Their necks could reach the tops of tall trees, allowing them to feed on leaves that no other animal could reach. Fossil evidence shows that their necks were made of many light but strong vertebrae, some of them hollow, reducing their weight so that they could lift and stretch them. They had small heads compared to their bodies, and their teeth were mostly peg-like or spoon-shaped, fit for stripping leaves rather than chewing. This meant they swallowed their food quickly and probably relied on huge stomachs to grind and digest the plant material. To support such massive bodies, their bones had air spaces inside them, making them lighter, and their circulation must have been powerful enough to send blood all the way up those towering necks. One of the most famous sauropods is Brachiosaurus, which lived in the late Jurassic period around 150 million years ago. Unlike most sauropods, its front legs were longer than its back legs, giving it a slightly upward sloping body posture, almost as if it were reaching toward the sky at all times. This shape made it different from Diplodocus, another sauropod of the same age, which had much longer tails and more even leg lengths. Diplodocus could sweep its long necks across a wider area closer to the ground, feeding on ferns and low trees, while Brachiosaurus could reach the highest vegetation. These differences show how sauropods divided the plant world among themselves, reducing competition and allowing many kinds to live side by side. In South America, another sauropod called Argentinosaurus reached sizes even greater than Brachiosaurus. Fossils suggest it might have weighed over 100 tons, making it one of the largest land animals that ever lived. These immense creatures must have moved in herds, not only for feeding but also for protection. Tracks found preserved in ancient mud show rows of sauropods walking together, adults in the front and back, and smaller juveniles kept safe in the middle. The world of dinosaurs was not only filled with plant-eating giants, but also with predators. This is where the theropods come in. The theropods were mostly meat-eaters, though some later species became omnivores or even plant-eaters. They walked on two strong legs, had sharp claws, and usually carried powerful jaws filled with sharp teeth. Their bodies were often built for speed and hunting, though not all were equally fast or equally large. The group includes some of the most well-known dinosaurs such as Tyrannosaurus Rex, Velociraptor, and Allosaurus. But theropods were a huge family with many different branches, ranging from chicken-sized hunters to beasts longer than buses. Allosaurus, which lived in the late Jurassic, around 150 million years ago, was one of the main predators of its time. It had strong hind legs, long arms with three-fingered hands tipped with claws, and a large skull with dozens of sharp teeth. Fossils show it was a cooperative hunter, possibly attacking large sauropods in packs, nipping at them until the prey was weakened. Its jaws were not as strong as those of Tyrannosaurus, but its teeth were serrated like steak knives, perfect for slicing through flesh. Later, in the Cretaceous period, Tyrannosaurus Rex appeared. Living about 68 to 66 million years ago, Tyrannosaurus was one of the most powerful predators to ever walk the earth. It stood about 12 feet tall at the hips, stretched about 40 feet long, and weighed as much as 10 tons. Its skull was massive, with teeth as long as bananas, built to crush bone. Unlike Allosaurus, it relied on its immense bite force to overpower prey. Studies suggest its bite was strong enough to crack through the armor of other dinosaurs and even break bones clean in half. Its small arms have often been a subject of curiosity, but scientists think they were still strong and may have been used to hold on to struggling prey. Despite its size, Tyrannosaurus could run at decent speeds, though probably not as fast as smaller predators. Theropods were not only killers, but also the ancestors of modern birds. Fossils discovered in China show small feathered theropods, such as Microraptor and Archaeopteryx, which had wings and could glide or fly short distances. These discoveries revealed that feathers did not first appear for flight, but likely for warmth or display, and later they were adapted for gliding and flight. This connection shows how dinosaurs were not only rulers of their time, but also gave rise to the creatures that still fill our skies today. While sauropods and theropods dominated with size and predation, another important group of dinosaurs developed heavy armor. These armored dinosaurs were plant-eaters that used thick plates, spikes, and clubs for protection against the meat-eating theropods. Among them were the stegosaurs, ankylosaurs, and nodosaurs. Stegosaurus, which lived in the Jurassic period around 150 million years ago, was a large herbivore with rows of tall plates running along its back and spikes on its tail. The plates may have been used for display, temperature control, or defense, while the tail spikes, sometimes called a thagomizer, were deadly weapons against attackers. Fossils show that Allosaurus, the predator of the same time, often received injuries that might have been caused by these spiked tails. Despite its heavy armor, Stegosaurus had a very small brain, not much larger than a walnut, which seems tiny for an animal weighing several tons. Yet, it survived for millions of years, showing that intelligence was not always necessary for success. In the later Cretaceous period, ankylosaurs took armor to the extreme. These low-slung dinosaurs were covered from head to tail in thick, bony plates, almost like a living tank. Their most striking feature was the large club at the end of their tails, formed from fused bone. With one swing, this club could break the legs of a predator like Tyrannosaurus. Ankylosaurs were slow-moving, but their defenses made them almost impossible to attack. Nodosaurs, close relatives of ankylosaurs, also had heavy armor but lacked the tail club. Instead, they carried rows of spikes along their sides, discouraging predators from biting. These armored dinosaurs show another way life adapted during the reign of dinosaurs. Instead of becoming giants like the sauropods or hunters like the theropods, they became walking fortresses that relied on protection. The rise of sauropods, theropods, and armored dinosaurs changed the landscape of Earth. Forests and plains became arenas where massive plant-eaters grazed, fast-moving hunters stalked, and heavily armed herbivores stood their ground. Each group developed its own strategies to survive. Sauropods relied on sheer size and herding, feeding high and low across the land. Theropods relied on teeth, claws, and speed, always pushing to catch the weak or unwary. Armored dinosaurs relied on defense, making predators think twice before striking. Together, they created ecosystems as rich and complex as anything seen today, if not more. Throughout their history, dinosaurs were also shaped by changes in climate, geography, and vegetation. During the Triassic period, the continents were joined together in one giant landmass called Pangaea, and early dinosaurs were smaller and less dominant. By the Jurassic period, the continents began to split apart, climates became wetter, and vast forests of conifers and ferns provided food for the rising sauropods. By the Cretaceous period, flowering plants had appeared, changing the diets of many herbivores and leading to even more diversity. This meant that sauropods had more competition from other plant-eaters, theropods faced new challenges and opportunities, and armored dinosaurs found new ways to thrive. Fossils give us glimpses of these lives. In the western United States, huge fossil beds reveal entire communities of dinosaurs, with bones of sauropods like Apatosaurus and predators like Allosaurus preserved together. In South America, gigantic titanosaur sauropods such as Argentinosaurus and Dreadnoughtus show how the southern continents became centers for dinosaur gigantism. In Asia, feathered theropods provide a direct link to birds. In Mongolia's deserts, fossils of Velociraptor locked in combat with Protoceratops reveal dramatic moments frozen in time. These finds remind us that dinosaurs were not abstract monsters, but real animals that lived, fought, fed, and died in dynamic worlds. The dominance of these groups also rested on their ability to reproduce. Dinosaurs laid eggs, and many species cared for their young. Fossilized nests of sauropods showed dozens of eggs laid in circular patterns, sometimes buried in sand or vegetation to keep them warm. Evidence from sites in Mongolia suggests that some theropods brooded their eggs like birds, sitting on nests with feathers spread to cover them. This care would have given hatchlings a better chance of survival in dangerous environments, where predators were always lurking. Even the armored dinosaurs left behind eggs, though less is known about how they raised their young. These reproductive strategies helped them maintain their populations for millions of years through changing environments and rising predators. The story of sauropods, theropods, and armored dinosaurs is not just about size or survival, but about variety. Sauropods range from the colossal Argentinosaurus to smaller, shorter-necked relatives. Theropods range from the towering Gigantismus of South America to the tiny Compsognathus, barely the size of a chicken. Armored dinosaurs range from the plate-backed Stegosaurus to the club-tailed Ankylosaurus. Their differences show how evolution branched into countless directions, filling every niche on land. Some grazed on low ferns, others browsed high trees, some chased prey in packs, others defended with armor, and some took to the skies with feathers. The land was filled with activity, noise, and struggle, a theatre of life where dinosaurs ruled in many ways. The rise of these dinosaurs also shaped other creatures. Mammals existed alongside dinosaurs for most of their reign, but they remained small and mostly nocturnal, living in the shadows of the giants. Only after the fall of the dinosaurs 66 million years ago did mammals begin to rise and diversify into the roles once filled by these rulers of the land. But while dinosaurs lasted, they were unmatched. No other land animals came close in size or in dominance. The sauropods towered above the trees, the theropods brought fear and danger, and the armoured dinosaurs showed resilience and defence. Together they created an age where land was not ruled by any single species, but by entire groups that had mastered different strategies of survival. Sauropods were among the most extraordinary animals to have ever lived on our planet. They were herbivores, meaning they lived by feeding on plants, yet their size and power made them stand out as some of the most impressive creatures in Earth's long history. These giants included well-known dinosaurs like Brachiosaurus and Argentinosaurus, animals so massive that they could stretch as tall as modern buildings and weigh more than dozens of elephants combined. They lived during the Mesozoic era, a period that stretched over many millions of years and was often described as the age of the dinosaurs. Within this span of time, sauropods evolved into some of the largest land animals ever to exist, filling forests, plains, and river valleys with their towering presence. To understand sauropods is to step into a world where the ordinary rules of animal life seem to bend. In today's world, the largest land animals are elephants, which may weigh up to several tons, but sauropods dwarfed even these. Argentinosaurus, one of the largest of them all, may have stretched close to 120 feet in length and weighed up to 100 tons. Standing next to such a creature would have made any human being feel as small as an insect. Its neck alone could stretch longer than a city bus, sweeping across treetops as it fed on leaves. Brachiosaurus, another well-known sauropod, stood so tall that it rivaled modern buildings several stories high, raising its neck like a living tower to graze on the highest branches of ancient forests. Their long necks were not just impressive in size, but also served a clear purpose. These animals needed to consume enormous amounts of food every single day just to survive. Their necks allowed them to reach across wide areas without moving their massive bodies too often. With a single sweep of the head, they could strip entire sections of trees, pulling down clusters of leaves and branches. This gave them access to food that other dinosaurs could not reach, making them rulers of the treetops in the prehistoric world. Their teeth were not sharp like those of carnivores, but rather spoon-shaped or peg-like, perfect for stripping leaves rather than chewing them. Instead of grinding food the way mammals do, sauropods often swallowed it whole, letting their massive digestive systems handle the process. Their stomachs and guts worked like huge fermentation chambers, slowly breaking down plant material and drawing out the energy needed to sustain such giant frames. What is even more fascinating is how these giants managed to move their enormous bodies. Despite their size, sauropods were built in ways that allowed them to walk with surprising efficiency. Their legs were column-like, thick and strong, shaped to carry incredible weight without collapsing. The bones in their limbs were dense and sturdy, but their skeletons also had special adaptations to keep them from being too heavy. Many sauropods had hollow spaces in their bones, much like the bones of modern birds, which reduced weight without sacrificing strength. This clever balance of strength and lightness made it possible for them to grow to such astonishing sizes. The world they lived in was also well suited to their needs. During the Jurassic and Cretaceous periods, when sauropods thrived, Earth's climate was generally warm, with vast forests of conifers, ferns and cycads stretching across the land. There were no icy poles as we know them today, and vegetation was abundant in many regions. This environment provided the endless supply of food that sauropods required. Water sources like rivers and lakes were also plentiful, which mattered greatly since such enormous animals would have needed large amounts of water to survive. Herds of sauropods might have wandered across these landscapes, travelling long distances in search of fresh growth, stripping trees bare and leaving behind trampled pathways through the vegetation. Fossil evidence suggests that sauropods often lived in groups, perhaps for protection or to aid in raising young. Travelling in herds would have made sense in a world filled with dangerous predators. Giant carnivores like Allosaurus in the Jurassic and later Gigantosaurus in the Cretaceous would have seen young sauropods as potential prey. By moving in groups, adult sauropods could have shielded their vulnerable young, forming protective circles around them if danger approached. The sheer size of a full-grown sauropod would have discouraged most predators from attacking. Few meat-eating dinosaurs would dare to face a creature weighing many dozens of tons, but young sauropods were small enough to be at risk until they grew large. One of the most striking features of sauropods was their necks, which in some species stretched more than 30 feet long. Scientists have long debated how these long necks were used. Some believe sauropods like Brachiosaurus held their necks upright, reaching into the highest trees like living giraffes, while others think their necks stretched out more horizontally, sweeping across broad areas of vegetation close to the ground. Either way, the long necks gave them an unmatched advantage in feeding. To support these enormous structures, sauropods had strong muscles, ligaments, and air-filled spaces inside the bones of the neck to reduce weight. This design allowed them to carry and move their heads without exhausting themselves. Their tails were just as remarkable. Long and whip-like, sauropod tails could stretch for dozens of feet behind them. These tails may have served as balance when walking, as defense against predators, or even as communication tools within herds. Some scientists have suggested that sauropods could snap their tails like giant whips, creating cracking sounds that might have warned predators or signaled other members of the group. Whether or not they used them this way, the tails of sauropods were an important part of their overall design, helping to balance their massive bodies. The growth of these creatures was another fascinating mystery. Sauropods hatched from eggs, just like other dinosaurs, and the eggs were relatively small compared to the adult size of the animal. A newly hatched Gigantosaurus may have been no larger than a small dog, yet within a few decades it grew into the largest land animal the world has ever seen. To grow so quickly, sauropods needed to eat constantly, and their bones show signs of rapid growth. Special tissues in their bones, similar to those found in birds, indicate that they could grow at astonishing rates, reaching adulthood much faster than reptiles typically do. This rapid growth may have helped them escape the most vulnerable stage of life, since a small sauropod would have been easy prey. Sauropods were also remarkable for how long they managed to dominate Earth's ecosystems. From the late Triassic period, around 220 million years ago, until the end of the Cretaceous period about 66 million years ago, they were a constant presence. Across this vast stretch of time, different groups of sauropods evolved and adapted to new environments. Diplodocus, with its slender body and long whip-like tail, thrived in the late Jurassic. Brachiosaurus, with its tall build and upright neck, lived during the same time. Later, giants like Argentinosaurus appeared in the Cretaceous, pushing the limits of size further than ever before. Even though new predators and competitors arose, sauropods continued to find ways to survive and remain dominant herbivores of their time. Their fossil remains have been found on every continent, showing just how widespread they were. In North America, the Morrison Formation has yielded countless sauropod fossils, including Diplodocus, Apatosaurus, and Brachiosaurus. In South America, especially in Argentina, paleontologists have uncovered fossils of Argentinosaurus and other titanosaur sauropods, some of the largest ever discovered. Africa has given us fossils of creatures like Jabaria and Paralititan, while Europe has revealed its own unique forms. Even in Antarctica, bones of sauropods have been found, proving that these animals adapted to many different climates and environments. The discovery of sauropod fossils has often been dramatic, sparking excitement and wonder. In the 19th century, when paleontology was still young, fossils of huge sauropods astonished scientists and the public alike. The sheer size of their bones, some longer than a person, challenged ideas about what animals could be. Skeletons of Diplodocus and Brachiosaurus, once mounted in museums, became symbols of prehistoric life, drawing crowds who marveled at their scale. More recently, discoveries of titanosaur fossils in South America have continued to reveal just how large sauropods could grow, with some bones so massive that they required heavy machinery to excavate. Life as a sauropod must have been both challenging and rewarding. On one hand, their size protected them from most predators and gave them access to food few other animals could reach. On the other hand, their enormous bodies required constant feeding and water. Moving across landscapes in search of resources, they likely followed migration routes, travelling seasonally to areas with enough vegetation to support their herds. The weight of their steps would have left deep impressions in the ground, and fossilised trackways discovered around the world give us clues about their movements. These tracks, sometimes stretching for hundreds of feet, show groups of sauropods walking together, young ones surrounded by adults, all moving in the same direction like a great caravan of giants. The physiology of sauropods also raises fascinating questions. How did such massive creatures pump blood all the way to their heads if their necks were held upright? Some scientists suggest that they had incredibly strong hearts, perhaps weighing hundreds of pounds, capable of generating the pressure needed to move blood to such heights. Others think that their necks may not have been held as vertical as once thought, which would have made circulation easier. The lungs of sauropods were also unusual. Evidence suggests that, like birds, they had air sacs connected to their lungs, creating a highly efficient breathing system. This would have allowed them to take in oxygen more effectively, which was crucial for supporting such large bodies. The skin of sauropods, though rarely preserved in fossils, has been found in some cases with impressions that show patterns of scales. Unlike mammals, they did not have fur, and unlike birds, they did not have feathers. Instead, their bodies were covered in tough, scaly skin that helped protect them from the environment. Some titanosaurs even had small bony plates called osteoderms embedded in their skin, possibly as an additional form of defense. Though not as heavily armored as some other dinosaurs, these features may have offered protection against predators or helped store minerals for their massive bodies. In terms of behavior, sauropods may have communicated with each other through sound and movement. The idea of them using low-frequency calls, similar to the infrasound produced by elephants, has been suggested. Such sounds could have travelled long distances, allowing herds to stay in contact even when spread across wide areas. Their sheer size also meant that any movements they made would have been felt through the ground, vibrations that other sauropods might have sensed. These forms of communication would have been useful for coordinating movements, warning of danger, or maintaining social bonds within the herd. Even though they were peaceful plant eaters, sauropods shaped the world around them in powerful ways. By feeding on vast amounts of vegetation, they influenced the growth and spread of plants. Entire forests would have been altered by their constant grazing. Trees adapted to grow taller and sturdier in response to their feeding, while plants closer to the ground would have been trampled or eaten in great quantities. Their dung, produced in massive amounts, fertilized the soil, spreading nutrients and seeds across the land. In this way, sauropods acted as ecosystem engineers, transforming their environments much as elephants and other large animals do today. The extinction of sauropods, along with other non-avian dinosaurs, came at the end of the Cretaceous period, around 66 million years ago, when a massive asteroid struck Earth. This event caused catastrophic changes to the climate, blocking sunlight, disrupting ecosystems, and wiping out many forms of life. For creatures as large as sauropods, the sudden loss of vegetation and collapse of food chains spelled the end. Yet, despite their extinction, their legacy lives on through the fossils they left behind, which continue to inspire awe and curiosity. The fascination with sauropods is not only scientific but also cultural. They have appeared in countless books, movies, and artworks, often portrayed as the ultimate symbol of prehistoric life. Standing tall and gentle, they capture the imagination as examples of life at its most grand scale. Children and adults alike are amazed when confronted with the skeleton of a sauropod in a museum, its long neck stretching overhead, its tail disappearing into the distance. These creatures remind us of a time when Earth supported life forms far beyond anything we see today, a reminder of nature's power to create giants. The study of sauropods continues to advance as new fossils are uncovered and new technologies are applied. Detailed scans of bones, analysis of microscopic structures, and computer models of movement and breathing all help scientists piece together the puzzle of how these giants lived. Each discovery adds another layer to our understanding, showing that sauropods were not just oversized animals, but finely adapted creatures that thrived in their environments for millions of years. Their story is one of evolution pushing the boundaries of size, function, and survival, creating beings that still stand unmatched in the history of land animals. The ancient seas were once filled with creatures of staggering size and power, animals that make the largest sharks and whales of today seem far less frightening in comparison. These were the marine monsters of the deep, predators that reigned in the oceans during times when the land itself was crawling with dinosaurs, and later when mammals were only beginning to make their mark on the world. From the monstrous Mosasaurus that swam during the late Cretaceous period to the enormous Megalodon that patrolled the oceans millions of years later, these creatures turned the waters of Earth into hunting grounds, where survival meant either being a predator of incredible size and skill, or constantly avoiding one. Mosasaurus was among the most fearsome of these ancient hunters. It lived around 70 million years ago during the closing chapters of the Age of Dinosaurs. Despite its name, which makes it sound somewhat like a dinosaur, it was not a dinosaur at all but rather a marine reptile, a close relative of modern snakes and monitor lizards. Its body could grow longer than 50 feet, making it larger than most living whales except the biggest ones like the blue whale. With a skull filled with sharp, conical teeth and jaws capable of swallowing prey nearly whole, Mosasaurus hunted fish, turtles, sharks, and even other marine reptiles. It was sleek, powerful, and built for ambush. Its strong tail propelled it through the water with speed, while its paddle-like limbs guided its movements. For any creature swimming in the same waters, the sudden appearance of such a beast meant almost certain death. Fossils of mosasaurs have been found across Europe, North America, and other parts of the world, showing that they were spread across much of the ancient seas and dominated the oceans in the last days of the dinosaurs. While Mosasaurus was the king of its time, the seas have hosted many rulers over the ages. Long before Mosasaurus, there were other giants such as the Pliosaurs. These were short-necked plesiosaurs with massive heads and terrifying jaws. One of the most famous was Leopleurodon, which could reach lengths of over 20 feet, though some estimates once claimed much larger sizes. Its head alone could stretch longer than the average human, with rows of teeth designed for ripping apart prey. Plesiosaurs like Leopleurodon swam during the Jurassic period, roughly 160 million years ago, and they were among the top predators of their age. They could ambush prey with powerful bursts of speed, using their 4 strong flippers to slice through the water, with surprising agility despite their size. Fossil evidence suggests they hunted fish, squid-like creatures, and even other marine reptiles, cementing their role as the apex predators of their ecosystems. As time passed, the ocean saw new hunters rise and older ones vanish. After the extinction of the dinosaurs around 66 million years ago, the seas slowly shifted to favour new types of predators. One of the most spectacular and frightening was the Megalodon, a shark so enormous that it dwarfed any living shark today. Megalodon lived between 23 and 3 million years ago, long after the dinosaurs had disappeared. Its name means big tooth, and that is no exaggeration. Fossilised teeth of Megalodon can be longer than 7 inches, far bigger than the teeth of the modern great white shark. These teeth are triangular, serrated like a steak knife, and built to slice through flesh and bone. From these teeth and other fossil evidence, scientists estimate that Megalodon could grow to lengths of 60 feet or more, with some estimates suggesting even larger. That would make it twice as long as a great white shark and easily one of the largest predators to have ever lived. Megalodon's jaws were so powerful that they could bite with a force far greater than any animal alive today. Estimates suggest that its bite could reach more than 40,000 pounds of pressure, enough to crush the bones of whales with ease. In fact, whales were its favourite prey. During the time of Megalodon, the oceans were filled with early ancestors of today's whales, many of which were smaller than modern ones, making them perfect targets. Fossil bones of whales from this period often carry the telltale marks of giant shark teeth, showing that Megalodon regularly hunted them. It would strike with speed and precision, delivering bites to cripple its prey before finishing them off. It was not only whales that had to fear Megalodon, but also large fish, seals, and even other sharks. Nothing was safe when such a monster prowled the waters. Megalodon's dominance lasted for millions of years, but like so many great predators before it, it eventually vanished. Its extinction around 3 million years ago has been linked to several factors. Changes in climate cooled the oceans, which may have reduced the number of warm, shallow seas where Megalodon thrived. At the same time, many of its whale prey began migrating to colder waters, where the giant shark may not have been able to follow as effectively. Competition from other rising predators, such as the ancestors of today's great white shark, may have also played a role. Whatever the combination of causes, the disappearance of Megalodon marked the end of one of the most terrifying chapters in ocean history. But the Megalodon and the Mosasaurus were not alone in making the oceans of the past deadly places. There were also the Ichthyosaurs, marine reptiles that resembled modern dolphins but were much larger and more reptilian in their features. Some species of Ichthyosaur reached lengths of over 60 feet, rivaling even the great whales of today. They lived from the early Triassic period, more than 200 million years ago, all the way into the late Cretaceous, although most species had vanished before Mosasaurus took over. Fossil evidence shows that Ichthyosaurs gave birth to live young, just like modern dolphins and whales, and they were swift swimmers built for chasing fish and squid. Some species had enormous eyes, which would have helped them see in the dim light of deeper waters, suggesting that they hunted at depths where other predators could not follow. While not always the apex predators, they were still among the most successful marine reptiles of their time. Alongside Ichthyosaurs and Plesiosaurs, the seas were also patrolled by long-necked plesiosaurs. Unlike the plesiosaurs with their huge heads, these had small heads at the end of extremely long necks, some stretching over 20 feet in length. The most famous of these is Elasmosaurus, which lived about 80 million years ago. With its tiny head and long neck, it probably hunted schools of fish, snapping them up quickly while keeping the bulk of its body at a distance. This design, however, made it vulnerable to the larger predators like Mosasaurus, which likely preyed on them when given the chance. Even beyond reptiles and sharks, other massive creatures left their mark in the seas. During the Devonian period, nearly 400 million years ago, the oceans were home to giant armoured fish called placoderms. Among them was Dunkleosteus, one of the earliest true giants of the seas. Dunkleosteus could grow up to 30 feet long, and instead of teeth, it had massive bony plates that formed a beak-like mouth. These jaws were incredibly strong, capable of biting through armour and crushing almost any prey. Fossils show that Dunkleosteus had a hinged skull that allowed it to open its mouth extremely fast, creating a suction force that pulled prey in before snapping shut with deadly strength. For tens of millions of years, it ruled as one of the most fearsome predators before eventually disappearing as newer fish species evolved. The pattern of the oceans across history has always been the same. One giant predator rising, dominating, and then eventually vanishing, only to be replaced by another. Each new age of the seas introduced creatures that seemed larger and more terrifying than what came before. The late Jurassic seas were ruled by pliosaurs, the late Cretaceous seas by mosasaurs, the Miocene and Pliocene seas by Megalodon. Each of these predators was perfectly adapted to its environment and prey, and each in turn left fossils that remind us of how dangerous the oceans once were. Even though these creatures are now gone, their presence still fascinates people today. Fossilized remains such as massive teeth of Megalodon, giant vertebrae of Mosasaurus, and enormous skulls of pliosaurs are displayed in museums, giving us a glimpse of the monsters that once swam where today there are only ordinary fish and whales. Scientists continue to study these fossils to better understand how these predators lived, hunted, and eventually died out. Every new discovery adds to the picture of ancient oceans filled with creatures so massive and fierce that they seem almost unreal. To swim in the seas during those times would have been a terrifying experience. Imagine waters filled not with harmless fish but with reptiles longer than buses, sharks larger than houses, and armoured fish with jaws that could shatter bone. The oceans were arenas of constant survival, where every creature either hunted or risked being hunted. The story of these marine monsters shows just how powerful and dangerous life beneath the waves once was, and how much the world has changed over millions upon millions of years. Predatory behemoths such as Tyrannosaurus Rex were some of the most dangerous and awe-inspiring creatures that ever lived on Earth. They walked the land millions of years ago during the long reign of the dinosaurs, and they ruled their world as unmatched hunters. Their very size, their sharp teeth, and the power of their jaws turned them into the masters of ancient landscapes. Tyrannosaurus Rex, often called the king of the tyrant lizards, stood as one of the most famous examples of these terrifying carnivores. It was not alone in this role, for other large predators filled the prehistoric plains, forests, and river valleys, with constant tension between hunter and hunted. Life during those ages meant that every creature, whether small or large, had to remain alert, for death could come swiftly in the form of a hungry predator. Tyrannosaurus Rex lived during the late Cretaceous period, roughly 66 million years ago, at the very end of the age of dinosaurs. This great beast grew to nearly 40 feet in length, stood more than 12 feet tall at the hips, and weighed as much as 7 or even 9 tons, making it one of the heaviest land predators ever to walk the earth. Its skull alone could measure nearly 5 feet long, and its massive jaws carried around 60 thick teeth shaped like steak knives, some longer than a human hand. When Tyrannosaurus Rex bit down, it did so with one of the most powerful bites known in the animal kingdom, crushing bone and tearing flesh with ease. The force of that bite has been estimated to be strong enough to break the bones of even the largest dinosaurs it hunted. Few animals in history have possessed such natural weapons, and fewer still used them with such deadly skill. The ancient plains and forests of North America, where Tyrannosaurus Rex roamed, were full of giant plant eaters that served as prey. Triceratops, with its 3 horns and large frilled head, was a common sight, and though it was armed, it was still vulnerable to a determined predator. Hadrosaurs, sometimes called duck-billed dinosaurs, gathered in herds and provided another major source of food. For a predator as large as Tyrannosaurus Rex, hunting a single small animal would not have been enough, so it went after these massive creatures, chasing them down or waiting to ambush them. Evidence from fossilized bite marks shows that Tyrannosaurus Rex often attacked living prey, but it also fed on carcasses when the chance arose. This balance of hunting and scavenging made it an extremely adaptable and successful predator. But Tyrannosaurus Rex was not the only predatory behemoth of its time. Throughout the long history of the dinosaurs, many other great carnivores rose to dominance. In earlier times, during the Jurassic period more than 150 million years ago, Allosaurus was the main hunter of the western North American landscapes. Allosaurus was smaller than Tyrannosaurus Rex, but it was still a dangerous predator, reaching lengths of 30 feet or more. Its skull was built lighter than that of Tyrannosaurus Rex, but it had sharp serrated teeth and strong arms with large claws. Allosaurus may have hunted in groups, bringing down enormous prey like the long-necked sauropods, including Diplodocus and Apatosaurus, that roamed the plains in massive herds. The sight of an Allosaurus pack attacking one of those huge creatures would have been one of the most dramatic scenes in Earth's history, a true clash of titans where survival was always uncertain. In the southern continents, another giant predator known as Gigantosaurus appeared during the late Cretaceous period, around 98 million years ago, in what is now Argentina. This dinosaur rivaled or even surpassed Tyrannosaurus Rex in length, growing more than 40 feet long, though it was slimmer and lighter in build. Its name means giant southern lizard, and it hunted the massive plant-eating dinosaurs of South America, such as Argentinosaurus, which was one of the largest creatures to ever walk on land. Hunting such an enormous animal would not have been an easy task, and it is possible that Gigantosaurus and others of its kind worked together, striking at their prey in coordinated attacks. Even if they did not hunt in groups, their sheer size and speed made them among the top predators of their time. Their teeth, long and serrated like carving knives, were designed not to crush bone but to slice through flesh, tearing huge wounds in their victims until blood loss and exhaustion brought them down. In Africa, another giant carnivore ruled the land during the mid-Cretaceous period about 100 million years ago. This was Carcharodontosaurus, whose name means shark-toothed lizard, because its teeth resembled those of a great white shark. This predator stretched more than 40 feet in length and weighed up to 7 tons. Its skull was long and narrow, filled with sharp teeth that could reach over 6 inches in length. It shared its world with Spinosaurus, another massive carnivore that was even longer, growing up to 50 feet in length. Unlike most predators, Spinosaurus lived a semi-aquatic life, hunting fish and perhaps ambushing other animals near rivers and swamps. The world of Africa during this time was one of the most dangerous ever known, filled with predators of almost unimaginable size. In Asia, another predator rose to great fame. This was Tarbosaurus, closely related to Tyrannosaurus Rex, which lived around 70 million years ago in what is now Mongolia. Tarbosaurus was slightly smaller than Tyrannosaurus Rex, but shared many of its features, including a powerful bite and strong legs built for hunting large herbivores. Fossil evidence suggests it preyed upon hadrosaurs and armored dinosaurs such as ankylosaurs, using its strength and speed to overpower them. The Mongolian plains, dry and open, provided a setting where Tarbosaurus could dominate the food chain much like its larger cousin in North America. The diversity of these predatory behemoths shows that nearly every continent had its own dominant carnivore during the age of dinosaurs. They filled the same role in ecosystems, standing at the top of the food chain, but each had its own style of hunting, its own body structure, and its own favoured prey. Some, like Tyrannosaurus Rex, relied on crushing power, while others, like Gigantosaurus, depended on slicing attacks. Still others, like Spinosaurus, developed specialised ways of living that set them apart from the rest. The world was not ruled by one single predator, but by many, each adapted to its own land and environment. The battles between predators and prey in these ancient times were constant struggles of strength, speed, and survival. Triceratops with its horns, ankylosaurs with their heavy armour and tail clubs, and sauropods with their sheer size and whipping tails were not defenseless. Every hunt carried risk, and a wounded predator might starve if it could not recover. This constant balance between attack and defense shaped the evolution of both sides. As prey animals grew larger or developed new defenses, predators adapted with sharper teeth, stronger jaws, or better hunting strategies. This endless arms race continued for millions of years, making the age of dinosaurs one of the most dynamic and dangerous periods in Earth's history. The world itself provided the stage for these behemoths. The continents were not in the same positions they are today, and climates were often warmer and wetter, supporting lush forests and wide open plains that could sustain giant animals. Rivers and swamps stretched across the land, creating habitats rich in life. Volcanoes erupted in some regions, reshaping the land and leaving behind fertile soil. Seas rose and fell, at times flooding lowlands and creating coastal environments where both land and marine predators thrived. The changing Earth forced animals to adapt, and those that could not keep pace vanished, leaving room for new species to rise and take their place. In such a shifting and challenging world, the largest and most adaptable predators often survived the longest. For millions upon millions of years, these predatory behemoths shaped the ecosystems they lived in. By hunting large plant eaters, they helped control populations and prevent overgrazing, which in turn allowed vegetation to recover and remain healthy. They were not simply killers, but key parts of their environments, influencing the survival of countless other species both directly and indirectly. Without predators at the top, the balance of life would have been very different. Fossils of their bones, teeth, and footprints remain today as evidence of their once dominant presence, scattered across deserts, cliffs, and badlands around the world. Each discovery adds more to our understanding of how they lived, hunted, and interacted with other creatures. The fascination with these predators continues in modern times because they represent power on a scale that humans can hardly comprehend. A Tyrannosaurus Rex towering over a human would make even the bravest person feel small and vulnerable. The idea of a Gigantosaurus chasing down a herd of Argentinosaurus is almost beyond belief, yet it was part of the daily life of the Cretaceous world. The teeth of Carcharodontosaurus, sharp as knives and the size of a man's hand, remind us of just how dangerous nature can be when shaped by millions of years of evolution. Even in museums, the skeletons of these creatures inspire awe, for they reveal the true size of animals that once lived and remind us that Earth's history is filled with stories far more dramatic than any fiction. Scientists continue to study these predators, using modern technology to unlock secrets hidden in their fossilized remains. CT scans allow researchers to look inside bones without damaging them, revealing the structure of brains and senses. Studies of teeth can show what kind of food they ate and how they processed it. Footprints preserved in ancient mud reveal how they walked, how fast they moved, and sometimes even how they hunted together. Isotope analysis of bones can provide information about diet and climate. With every new technique, the picture of these predators becomes clearer, showing not just monsters but living animals that hunted, rested, fought, and died in worlds long vanished. The story of the predatory behemoths is also a story of extinction. 66 million years ago, at the end of the Cretaceous period, a massive asteroid struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equal to billions of nuclear bombs, sending fire, shockwaves, and global darkness across the planet. The ecosystems that had supported Tyrannosaurus Rex and countless other dinosaurs collapsed in a matter of years. With plants dying, herbivores starved, and with herbivores gone, the great predators followed them into extinction. The reign of the predatory behemoths ended suddenly and dramatically, leaving behind only their fossilized bones as records of their time on Earth. Yet even in extinction, their legacy lives on. Birds, which are the descendants of smaller theropod dinosaurs, are a direct link to these ancient predators. Every time a hawk dives for prey, or an eagle spreads its wings, it carries a shadow of the great carnivores that once dominated the land. In that sense, the predatory behemoths are not entirely gone, for their bloodline continues in a new form, smaller and lighter but still driven by the instincts of hunters. Across the span of Earth's history, few creatures have matched the scale, power, and presence of Tyrannosaurus Rex, Gigantosaurus, Spinosaurus, Carcharodontosaurus, and their kin. They were the ultimate expressions of predation in their time, shaped by evolution to fill the role of top hunter with unmatched success. Their bones tell stories of survival and struggle, of battles fought on ancient plains, and of worlds lost to time. The age of the predatory behemoths remains one of the most remarkable chapters in the natural history of our planet. Flying giants were some of the most extraordinary creatures ever to appear on this planet. They belonged to a group of reptiles called pterosaurs, and among them were species so large that their wings stretched wider than the wings of a small airplane. These were not birds and they were not bats, but rather their own distinct branch of life, cousins to the dinosaurs that shared the same prehistoric world. They rose into the air in times when forests, swamps and deserts were filled with strange plants and animals. Among the largest of these flying reptiles was Quetzalcoatlus, a creature named after the feathered serpent god of ancient Mexico. Its wings are believed to have spanned more than 30 feet from tip to tip, making it the largest known flying animal in Earth's history. To picture such a reptile soaring above ancient plains is to think of something so massive yet so graceful that it challenges modern understanding of flight. The earliest pterosaurs appeared in the Triassic period, more than 200 million years ago. This was a time when the first dinosaurs were just beginning to spread across the supercontinent of Pangaea. These early flying reptiles were smaller than the later giants, with wingspans closer to the size of modern seabirds. Yet even in their smaller forms they were already testing the skies, gliding above rivers and coasts, hunting for fish and insects. Over millions of years, pterosaurs grew in size and diversity. By the time of the Jurassic period, about 150 million years ago, some had already reached impressive dimensions. Their bones, light and hollow, allowed them to be large without being too heavy to fly. Their wings were formed from a thin membrane of skin stretched along a greatly elongated fourth finger, creating a structure very different from the feathered wings of birds. Quetzalcoatlus lived during the late Cretaceous period, roughly 68 to 66 million years ago, in the final age before the great extinction event that ended the reign of dinosaurs and their relatives. Fossils of this flying giant were first discovered in Texas in the early 1970s by a young graduate student named Douglas Lawson. He found fragments of a huge wing bone and parts of a skull that hinted at an animal larger than any bird or bat. The remains were so astonishing that at first some scientists doubted whether such a creature could truly have flown. Yet careful studies of the bones, the lightweight structure, and comparisons with modern animals convinced experts that Quetzalcoatlus was indeed capable of powered flight, though how exactly it launched itself into the air has long been debated. The size of Quetzalcoatlus is almost beyond belief. With a wingspan stretching more than 10 meters, or over 30 feet, it rivaled the length of a small bus. When standing on the ground, supported by its long and sturdy forelimbs, it may have stood as tall as a giraffe, reaching heights of 5 to 6 meters. Its neck was long and slender, balancing a head that stretched nearly 3 meters from the tip of its snout to the back of its skull. The jaws were toothless, but long and sharp-edged, like a giant spear, suggesting that it may have used them to grab prey such as fish, small dinosaurs, or carrion left behind by larger predators. Other pterosaurs, though not quite as immense as Quetzalcoatlus, were still gigantic by modern standards. Hatzegopteryx, discovered in what is now Romania, may have been of similar size, though with heavier bones and a thicker skull. Pteranodon, which soared over the seas of North America about 86 to 84 million years ago, had wings spanning over 20 feet and is among the most famous of the group, often pictured with its backward-pointing crest. Tropiognathus from South America carried large crests on its snout and flew with wings almost 30 feet across. These animals showed that the skies of the Cretaceous were not filled only with small flapping creatures, but also with enormous gliders whose shadows could darken the ground. The flight of such giants has been a puzzle for scientists. Modern birds with wings approaching even half the span of Quetzalcoatlus, such as albatrosses, are already pushed to the limits of what is possible for flight. Yet pterosaurs had a design different from birds. Their wings were membranes, more flexible and possibly more efficient at gliding than feathers for such large surfaces. Their bones were filled with air sacs connected to the lungs, reducing weight and helping them breathe with high efficiency. Some studies suggest they could launch themselves by vaulting into the air with all 4 limbs, pushing off powerfully before spreading their vast wings. Once airborne, they may have soared on warm rising air currents, much like vultures or condors today, covering great distances with little effort. Life in the skies for these giants was not without dangers. Storms could force them down, and on the ground they may have been vulnerable to predators such as tyrannosaurs or large dromaeosaurs. However, their size alone would have made them intimidating to most threats. A standing Quetzalcoatlus was a towering presence, and its sharp beak could have been used as a weapon if necessary. Its long wings could fold tightly when walking, allowing it to move in a strange quadrupedal stance across open plains. This ability to both fly and walk effectively gave it freedom to explore many habitats, from coastal cliffs to inland river valleys. The diet of Quetzalcoatlus has been widely debated. Some paleontologists once imagined it as a fisher, skimming the surface of lakes and seas with its beak like modern skimmer birds. Later studies suggested that such a lifestyle would be difficult given its large size and heavy skull. Another idea is that it hunted like a stork, walking along riverbanks and floodplains, snapping up small vertebrates, amphibians, or even hatchling dinosaurs. Still others suggest it was a scavenger, soaring high and using its keen eyesight to locate carcasses. Perhaps it did all of these things depending on opportunity, for such a large animal would need a flexible diet to survive. The discovery of Quetzalcoatlus and other giant pterosaurs has changed the way people think about the limits of flight. Before these fossils were known, the largest known flying animals were birds like the extinct Argentavis, a giant vulture-like bird from South America with a wingspan of around 23 feet. To realize that reptiles had flown with wings 10 feet wider than that is to see how nature experimented with extreme designs. These animals show that the sky of the Cretaceous was a dynamic and competitive space where different groups of creatures developed astonishing adaptations. The world they lived in was also different from today. During the late Cretaceous, much of North America was split by an inland sea, creating long coastlines and fertile plains. Warm climates allowed lush vegetation to grow, supporting herds of dinosaurs that in turn supported predators and scavengers. Flying giants like Quetzalcoatlus would have used the rising warm air over these plains to travel long distances, perhaps migrating between feeding grounds. Fossil evidence from Texas suggests they lived in regions once covered by river deltas, where food would have been plentiful. Beyond their biology, the very presence of such animals inspires wonder about evolution. They represent a line of reptiles that took to the air long before birds and bats. For more than 150 million years, pterosaurs dominated the skies. They evolved countless shapes and sizes, from tiny species no larger than a sparrow to the gigantic azhdarchids like Quetzalcoatlus. Their variety shows how adaptable life can be, filling niches from insect eaters to fish hunters to colossal gliders. When the mass extinction struck 66 million years ago, they disappeared along with the non-avian dinosaurs, leaving birds as the only surviving line of flying vertebrates from that age. The fossils of these creatures are delicate, for their bones were hollow and fragile. Often they are found crushed or incomplete, making reconstructions challenging. Yet even fragmentary remains can reveal much. A single bone of Quetzalcoatlus can be longer than a human arm, thin as a shell yet strong enough to support the weight of flight. Computer models and wind tunnel tests have been used to imagine how their wings might have functioned. Artists and scientists together bring them to life, creating images of vast reptiles soaring across prehistoric skies, their wings casting shadows over dinosaurs below. The size comparisons help one appreciate their scale. A Quetzalcoatlus flying above would have been larger than a Cessna light airplane. Its wingspan would stretch across a tennis court. Its head alone was longer than a human adult. Standing next to one on the ground would have been like standing beside a tall giraffe. Only this giraffe could fold out massive leathery wings and rise into the sky. Such comparisons make the reality of these animals easier to grasp, even if they remain creatures of a distant past. These giants also raise questions about the limits of animal design. How large can a flying creature truly be? What constraints do air, muscles, and bones place on size? Quetzalcoatlus seems to have pushed close to that boundary. Birds today show that wingspans much greater than 12 feet are rare, and those that do exist, like the wandering albatross, rely on gliding over oceans with minimal flapping. For a reptile to reach wings 3 times that span shows a remarkable evolutionary path. Some experts argue that Quetzalcoatlus may have spent much of its life soaring, avoiding energy-intensive flight. Others think it was a strong flyer capable of powered movement, though only for limited bursts. Either way, its size shows nature's capacity to stretch possibilities. The study of these flying giants continues to evolve. New finds, new techniques, and new debates keep reshaping the image of Quetzalcoatlus and its kin. Each fossil unearthed from ancient rock adds pieces to the puzzle, allowing a clearer picture of a creature that lived and died millions of years before humans. They are reminders of worlds that existed long before human history, worlds where the skies were filled with wings far larger than anything seen today. The name Quetzalcoatlus carries symbolic weight. Named after Quetzalcoatl, the feathered serpent god worshipped by ancient peoples of Mesoamerica, it ties the scientific discovery to human mythology. Though separated by tens of millions of years, both the creature and the god inspire awe and wonder. The fossilized bones speak to the reality of a giant reptile, while the name recalls the stories humans have told about beings that ruled the skies. It is as if the memory of flying serpents found in myth has an echo in the fossils buried in stone. Tyrannosaurus was one of the most powerful and fearsome animals ever to set foot on the Earth. Among this group, the most famous of all was Tyrannosaurus Rex, the word rex in Latin meaning king. Today almost everyone simply calls it T-Rex or T-Rex, a name that has become so well known that even children recognize it. This great predator has left behind more fossils than most other giant hunters, which has allowed scientists to study it more than almost any other dinosaur. Its fossil bones show that it once roamed across the lands that are now part of Western North America. But in the final days of the dinosaurs, that region was not the single solid continent we know now. Instead, it was part of a separate landmass called Laramidia, a long strip of land bordered by an inland sea. Unlike many of its close relatives that were found only in certain areas, Tyrannosaurus was spread across a wide range, and its fossils have been uncovered in many different layers of ancient rocks. These rocks date to the very end of the Cretaceous period, roughly between 73 and 66 million years ago. A few scattered discoveries even suggest it might have appeared a little earlier. It was the last and greatest of its family line, standing as one of the very last dinosaurs before the massive extinction event that swept away almost every giant reptile at the close of the Cretaceous world. This predator was a true two-legged hunter. It stood upright on its strong and muscular back legs, balancing its huge body with a heavy tail. Its skull was massive, armed with jaws filled with teeth as sharp as knives, while its front arms were tiny but surprisingly strong for their small size. Each of these short arms ended with two curved claws that were built for grasping. Some of the largest skeletons ever found show that Tyrannosaurus could grow more than 40 feet long, and some estimates suggest certain individuals might have reached as much as 43 feet. At the hips, they may have stood up to 13 feet tall, towering over almost everything else around them, and their bodies could have weighed nearly 9 tons. Although a few other giant predators in the age of dinosaurs may have matched it in size, none could surpass its reputation. Scientists believe its bite was the strongest of any animal that ever walked on land, strong enough to crush bone with a single snap of its jaws. In its world, Tyrannosaurus was the top hunter, the king of its ecosystem. It likely hunted many kinds of large plant-eating dinosaurs, including the duck-billed hadrosaurs, the horned ceratopsians with their great frills and horns, the armored ankylosaurs with their clubbed tails, and perhaps even the young of long-necked sauropods. For years, some experts argued that it may not have hunted at all, but lived mostly by scavenging carcasses. The debate lasted for decades, but most scientists now believe the truth lies in between. Tyrannosaurus was both a hunter and a scavenger, seizing whatever meals it could find. The fossils of Tyrannosaurus Rex are some of the best preserved among all dinosaurs. A number of skeletons have been uncovered in excellent condition, and in some rare cases traces of soft tissues and even proteins have been detected. Because of this rich fossil record, scientists have been able to study nearly every part of its body, from its bones and muscles to the ways it may have grown and moved. Yet many mysteries remain. Some experts still argue about how fast it could run, how exactly it fed, and what its life cycle looked like. There is also continuing debate about where exactly it fits in the family tree of meat-eating dinosaurs. The Asian predator Tarbosaurus bataar is considered by many to be so closely related that some think it should be placed in the very same genus as Tyrannosaurus. Other fossils once thought to represent entirely different species have been reclassified as belonging to Tyrannosaurus itself. More recently, the suggestion of a new species named Tyrannosaurus macraensis has stirred controversy, as not all experts agree it deserves to be separated from T-Rex. From the early years of the 20th century onward, Tyrannosaurus has held a powerful grip on the imagination of scientists and the public alike. The writer Riley Black once described it as the ultimate dinosaur, a fitting title for an animal so awe-inspiring. Its skeletons are often the star attractions in museums of natural history, drawing countless visitors eager to stand before its towering bones. Beyond the world of science, T-Rex has become a true cultural legend. It has stormed across the pages of books, appeared in television programs, and of course claimed its place in the famous Jurassic Park films, where it became the symbol of dinosaur power. The history of its discovery stretches back to the late 19th century. In the summer of the year 1874, a student named Peter T. Dotson uncovered a single tooth of what would later be recognized as Tyrannosaurus Rex on South Table Mountain in the state of Colorado. In the early 1890s, the paleontologist John Bell Hatcher collected bones in Wyoming that were first thought to belong to some other creature, but are now understood to have been part of T-Rex. Then, in the year 1892, the famous fossil hunter Edward Drinker Cope discovered two enormous vertebrae, which he wrongly believed came from a horned dinosaur. He gave them the name Manospondylus gigas, which means giant porous vertebra. It was only years later, in 1907, that scientists realized these bones actually came from a mighty meat-eating dinosaur. In the year 1917, the paleontologist Henry Fairfield Osborn noticed how similar these bones were to those of T-Rex, though he did not fully combine the names. Decades later, in the year 2000, a partial skeleton of Tyrannosaurus was found near the possible site of Cope's original discovery, bringing fresh attention to this old puzzle. The true rise of Tyrannosaurus began in the early 20th century with the discoveries of Barnum Brown, a field fossil hunter working for the American Museum of Natural History. In 1900, Brown dug up the first partial skeleton of Tyrannosaurus in Wyoming. 2 years later, in 1902, he found another partial skeleton in the Hell Creek Formation of Montana, which included more than 30 fossil bones. Writing about the find, Brown described the bones with wonder, noting their huge size and strength. In 1905, Henry Fairfield Osborn, who was then the head of the museum, officially named the new species Tyrannosaurus Rex. The name came from Greek and Latin, combining tyrannos, tyrant, sauros, lizard, and rex, king, making the full meaning king tyrant lizard. This name showed the dinosaur's great strength and rule. In that same year, Osborn also gave another specimen the name Dinosaurus imperiosus, but in 1906 he realized both skeletons belonged to the same animal and chose the name Tyrannosaurus to stay. Later, in 1941, the first T-Rex skeleton was sold to the Carnegie Museum of Natural History in Pittsburgh for $7,000. The bones of Dinosaurus later went to London's Natural History Museum, and its name inspired later fossil hunters in naming new tyrannosaurids. For many years, starting from the 1910s until after the 1950s, the skeletons found by Barnum Brown remained the only known examples of this dinosaur. The money troubles of the Great Depression and the World Wars made fossil hunting difficult, and it was not until later in the 20th century that new finds were made. But by then, Tyrannosaurus Rex had already taken its place as one of the most famous creatures of the ancient world, a true king among dinosaurs whose fame has never faded. Starting in the 1960s, scientists and fossil hunters began to take a new interest in the mighty Tyrannosaurus. This fresh excitement led to the finding and digging up of more than 40 skeletons across the western lands of North America, with some being as little as 5% complete and others reaching as much as 80% complete when counted by bones. In the year 1967, Dr. William McManus dug up a partial skeleton known as Moore 008. This fossil was only about 15% complete, yet it was important because it included a skull that was later rebuilt and put on display at the Museum of the Rockies, where it still stands as a main attraction. The 1990s became something of a golden time for Tyrannosaurus finds. In those years, nearly twice as many skeletons were found as in all the years before, including the two most complete examples ever dug up. These two were later given the famous names Sue and Stan. On August 12th of the year 1990, Sue Hendrickson, an amateur fossil hunter, came across what would become the largest and most complete Tyrannosaurus skeleton ever found. This amazing fossil was about 85% complete and found in the Hell Creek Formation. It was given the name Sue after its finder. However, Sue's find quickly became tied up in a long and bitter legal fight over ownership. In the year 1997, the courts ruled that the skeleton belonged to Maurice Williams, the man who owned the land where it had been uncovered. Later that year, Sue was sold at an auction for the shocking sum of $7,600,000, bought by the Field Museum of Natural History in Chicago. At that time, Sue became the most expensive dinosaur skeleton ever sold, a record that lasted until the year 2020, when the skeleton named Stan was sold for $31,800,000. The process of getting Sue ready for display was just as amazing as the find itself. Between the years 1998 and 1999, staff from the Field Museum spent more than 25,000 hours carefully removing the rock and dirt from the bones. Once cleaned, the bones were sent to New Jersey, where experts built the supporting frame. From there, the mounted skeleton was brought back to Chicago for final setup. On May 17th of the year 2000, Sue was shown to the public, becoming one of the museum's greatest attractions. Studies of Sue's bones showed that this mighty hunter had reached full size at around 19 years of age and lived until about 28 years old, making her the longest-lived Tyrannosaurus known so far. Another famous skeleton, named Stan, was found in the year 1992, also in the Hell Creek Formation. This fossil, discovered by Stan Sacrison, was about 70% complete, with 199 bones recovered. Stan is special not only for its completeness, but also for the signs of a rough life kept in the bones. The skeleton shows proof of broken ribs that healed, a broken neck that also healed, and even a giant hole at the back of the skull, nearly the size of a Tyrannosaurus tooth. This shows that Stan had survived fierce fights, likely with other tyrannosaurs. In the year 1998, a 20-year-old named Bucky Derflinger spotted a Tyrannosaurus toe bone sticking out of the ground, making him the youngest person ever to find such a fossil. His find was named Bucky in his honor. This particular Tyrannosaurus was a young adult standing about 3 meters tall and stretching around 11 meters in length. What made Bucky even more special was the keeping of its wishbone, known as the furcula, which had never before been found in a Tyrannosaurus. Today, Bucky is proudly displayed at the Children's Museum of Indianapolis. The summer of the year 2000 brought another amazing find, when a team led by Jack Horner found 5 Tyrannosaurus skeletons near the Fort Peck Reservoir. Just a year later, in 2001, a team from the Burpee Museum of Natural History found a half-complete skeleton of a young Tyrannosaurus in the Hell Creek Formation. This fossil was first thought to belong to a smaller species called Nanotyrannus, but further study showed that it was most likely a young Tyrannosaurus. The skeleton was named Jane and remains the most complete young Tyrannosaurus ever found. Jane is now shown at the Burpee Museum. In 2002, another skeleton was found by amateur collectors Dan Wells and Don Wyrick. This skeleton, named Wyrex, had 114 bones and was 38% complete. Its dig finished in 2004, and it became the first Tyrannosaurus dig to be shown live online, with daily photos, reports, and even videos. By the year 2006, Montana State University said that it had the largest Tyrannosaurus skull ever found, measuring about 1.5 meters in length, from the specimen MOR 008. Later checks showed that another skull from specimen ELAC 23844 was a little longer, at 1 meter and 36 centimeters, while Sue had the widest skull ever measured, at over 90 centimeters across. Not only bones, but also footprints have been linked to Tyrannosaurus. The first footprint believed to belong to this dinosaur was found in New Mexico in the year 1983 by Charles Pillmore. At first, it was thought to belong to another kind of dinosaur, but later studies showed it had features special to Tyrannosaurus feet, such as a clear heel and possible trace of a 4th toe. This footprint, named Tyrannosaurus pillmorae, was made on a muddy wetland floor during the late Cretaceous and measured 83 centimeters in length and 71 centimeters in width. Another possible footprint came to light in the year 2007, reported by British fossil expert Phil Manning, found in Montana's Hell Creek Formation. This track was smaller, about 72 centimeters long, and while it has not been proven for sure to belong to Tyrannosaurus, no other hunter of similar size is known from that area. In the year 2016, fossil experts Scott Persons and Phil Curry studied a line of footprints in Glen Rock, Wyoming, from the Lance Formation, dating to the very end of the Cretaceous period. These tracks were thought to belong either to a young Tyrannosaurus or perhaps the debated Nanotyrannus. By studying the spacing and depth of the tracks, they guessed that the dinosaur walked at a speed between nearly 3 and 5 miles per hour and had hips standing between 1.5 and 2 meters high. A later study in 2017 suggested that the animal may have moved even faster than first thought, maybe by 50 to 80% more than earlier guesses. Through these finds, skeletons, skulls, and even footprints, the mighty Tyrannosaurus has become more than just an ancient monster. Each find adds another piece to the story of one of the most powerful and interesting creatures ever to walk the earth. Tyrannosaurus Rex was without doubt one of the biggest and scariest land-living meat-eaters that ever walked the earth. Among the many skeletons that have been found, one of the most famous and most complete is the one called Sue, officially listed as FNHPR 2081. Sue now stands proudly in the Field Museum of Natural History in the city of Chicago. When alive, Sue reached a length of about 12 and a bit meters, which is roughly 40 feet, and stood at the hips between just under 4 meters tall, or about 12 to 13 feet. Scientists have closely studied Sue's bones with many methods, and the results show that this huge hunter may have weighed around 8.5 metric tons, which equals many thousands of kilograms of pure prehistoric muscle and bone. Another giant rival to Sue was a skeleton that scientists nicknamed Scotty, listed as RSM P2523.8. Scotty is kept at the Royal Saskatchewan Museum. According to measurements, Scotty was even longer than Sue, reaching an amazing 13 meters, or about 43 feet from nose to tail. By figuring out the body weight from the thickness of the leg bones, especially the thigh bone, experts decided that Scotty was the heaviest Tyrannosaurus ever found, weighing almost 9 metric tons, a massive weight that makes it one of the greatest hunters in Earth's history. Not every Tyrannosaurus was as huge as Sue or Scotty. Grown ones came in many different sizes. Over the years, scientists have made different guesses about the average weight of a grown Tyrannosaurus. Some earlier studies said certain ones could weigh as little as 4.5 tons, while others said more than 7 tons. Today, most experts think that normal grown ones weighed between 5.5 and about 8 tons, still making them some of the largest meat-eaters ever to walk the land. Interestingly, a study printed in the year 2024 said there was little proof that males and females were always different in size, meaning both could grow equally large. One of the most eye-catching parts of Tyrannosaurus was its head. The biggest skulls found measure about 1.5 meters long, or a little more than 5 feet. To make such a giant skull easier to carry, nature gave it large openings called windows, which made it lighter. But the skull of Tyrannosaurus was unlike those of other big hunters of its time. It was wide and heavy at the back but narrow at the front, giving it excellent two-eyed vision, allowing it to see prey with deadly sharpness. The skull bones were thick, with some joined together for extra strength, but many were filled with tiny air spaces like a honeycomb, which made the skull lighter. All of this gave Tyrannosaurus one of the strongest bites in the animal world, far stronger than any of its close relatives. The front of the upper jaw was U-shaped, not V-shaped like in most other hunters, which let it tear away bigger pieces of flesh and bone in one bite, even though it put more pressure on the front teeth. Its teeth themselves were marvels of natural design. They came in different shapes and sizes depending on where they were in the mouth. At the very front of the upper jaw were 4 tightly packed teeth on each side. These were D-shaped in cross-section, with ridges along the back and tips shaped like chisel blades. They curved backward, which stopped them from breaking when Tyrannosaurus bit down and pulled back with great force. The rest of the teeth were thick, cone-shaped and deeply set, often called lethal bananas rather than sharp daggers, because their size and strength made them perfect for crushing bone. Grown Tyrannosaurus had 12 teeth on each side of the upper jaw and 13 in the lower jaw's front part. The biggest tooth ever found, including its root, was about 30 centimeters long, making it the largest meat-eating dinosaur tooth ever discovered. The lower jaw itself was strong and grew deeper toward the back, adding even more crushing power to the bite. The jaws also had many small holes called foramina, which may have held nerves and blood vessels, possibly giving Tyrannosaurus a scent system like crocodiles, or even lips and soft tissues around its teeth. The backbone of Tyrannosaurus was a wonder of design. Its spine had 10 neck bones, 13 back bones, and 5 fused hip bones. The number of tail bones is not certain, but there were likely at least 40, and in Sue's case, 47 tail bones were kept. The neck curved into an S shape, short but very strong to hold up the heavy skull. The body bones were strong yet had air sacs that made them lighter. Strong tendons attached to the spines of the backbones, making the body sturdy while still reducing extra weight. The tail was long and heavy, working both as a balance for the giant head and as a place for the strong muscles that moved the back legs. The belly was protected by nearly 20 pairs of bony plates known as belly ribs, forming a shield-like cover across the underside. The shoulders of Tyrannosaurus were large, with shoulder blades longer than the short front arms. The front arms themselves were famously tiny compared to the rest of the body. The upper arm bone was short and thick, while the lower arm bones were even shorter and straight. Each hand had only 2 strong fingers with claws, though a small leftover of a third finger was still in the bones, no longer useful but showing its ancestry. The hip bones were massive, with the main bone stretching long and tall, giving wide spaces for the big muscles of the back legs. The pubic bone ended in a large boot-shaped piece, while the other hip bone stretched backward in a thin line. The back legs of Tyrannosaurus were very long compared to its body, giving it surprising speed for such a heavy animal. The foot bones showed a special design called the arctometatarsalia condition, where the middle toe bone was pinched near the ankle, a design that made the foot stronger and better able to hold the animal's huge weight. Many bones in the skeleton were hollow, keeping the animal lighter than if they were solid without losing strength. Altogether, Tyrannosaurus Rex was a creature that joined size, strength, and design in a way almost no other animal in history did. From its crushing teeth and powerful jaws to its tall frame and strong legs, every part of its body showed the story of a hunter that ruled its world with frightening power. Tyrannosaurus has a very special place in dinosaur science because it is the standard example, or the type, of its whole group. This great dinosaur gives its name to the larger group Tyrannosauridae, the family Tyrannosauridae, and the smaller subfamily Tyrannosaurini. In simple words, scientists use Tyrannosaurus as the main example to decide whether other dinosaurs belong in the same family or not. Some of its close relatives include Daspletosaurus, which lived in North America, and Tarbosaurus, which came from Asia. At times, these relatives were even thought to be the same as Tyrannosaurus, though many experts now see them as separate but very similar animals. For a long time, scientists thought Tyrannosaurids came from older, very large hunters like Megalosaurs and Carnosaurs, but newer finds show that they actually belonged with the smaller, lighter-built dinosaurs known as Coelurosaurs. The very first members of this group were the crested Proceratosaurids, small and lightly built hunters. Over time, more developed groups appeared, like the Pantyrannosaurs, which showed special changes in their hips, skulls, and limb shapes. Tyrannosaurs began as small hunters, but at least some of them grew much bigger by the early Cretaceous period. Their rise may have been linked to the fall of other great hunters, such as the Allosaurs and Megalosaurs, which lost their leading role during the early part of the late Cretaceous period. Tyrannosauroids can be known by certain details of their skull and skeleton, like their joined nasal bones and the special setup of their teeth. More developed types, such as Pantyrannosaurs, had even more unusual features. Their hip bones had special shapes, their nasal bones looked like an hourglass, and some of them had a foot structure called an arctometatarsus that helped with running. Some also began showing shorter arms with weaker build compared to their legs, a pattern that carried on in their later family. Other features, like rough nasal textures, smaller holes in their lower jaws, and special bone shapes around the eyes and skull, all helped scientists follow their path of change. Studies of family trees show that Tarbosaurus bataar from Mongolia is very closely related to Tyrannosaurus rex, almost like a sister species. Another key tyrannosaur, Lithranax, helped prove that both Tyrannosaurus and Tarbosaurus shared close ties with another Asian giant, Zhuchengtyrannus. In 2016, researchers such as Steve Brusata and Thomas Carr even suggested that Tyrannosaurus itself may have first come from Asia before moving into North America. In 2013, Lowen and his team published a detailed family tree of tyrannosaurids that confirmed many of these ties. Later, in 2024, a new species called Tyrannosaurus macraensis was named, and the study once again showed Tyrannosaurus as being closely related to Tarbosaurus and Zhuchengtyrannus. Another group of tyrannosaurs, including Daspletosaurus and Thanatotherists, formed a branch known as Daspletosaurinae, which shows just how many family splits there were among these great hunters. The naming of these dinosaurs has its own story full of twists and debates. In the year 1955, the Soviet scientist Evgeny Maleev named a dinosaur from Mongolia as Tyrannosaurus bataar. Just 10 years later, in 1965, it was given its own separate genus and renamed Tarbosaurus bataar. Most paleontologists accept the split, though some, including Thomas Holtz and Kenneth Carpenter, believe the likeness is so strong that the two should stay under the same genus name. In the 1970s, several supposed species of Tyrannosaurus were named in China, such as T. lanpingensis in 1975, T. turpanensis in 1978, and T. luanchuanensis in 1979. However, these were named only from single teeth or bones and without full studies. Later on, in 2004, Thomas Holtz decided that all of them were really just junior names of Tarbosaurus bataar, meaning they were not true separate species. In the year 2000, a large toe or finger bone was found in Russia and first thought to belong to Tyrannosaurus. But by 2004, it was rethought as possibly belonging to a ceratosaur instead. Later reviews judged it too uncertain to place in any one group, and it remains unknown. In 2001, another paleontologist named teeth and bones from China as a new species, Tyrannosaurus juchengensis. But later finds in the same area showed that they probably belonged to Jucheng tyrannus, a large Asian tyrannosaur named in 2011. The supposed T. juchengensis is now seen as a doubtful name. Other puzzling fossils also make the story harder. In 2006, a skull bone called a lacrimal from Montana was described and may be linked to Tyrannosaurus. It was found long ago with the remains of Dinosaurus, a giant crocodile, but had not been described for decades. This bone was big enough and shaped enough like those of Tyrannosaurus Rex to suggest that giant tyrannosaurids might have lived earlier than thought, around 75 million years ago, during the Campanian stage, instead of only in the later Maastrichtian stage between 68 and 66 million years ago. The problem is that the exact site and age of the bone remain unknown, leaving scientists careful. In 2018, another study described a tooth from Montana that looked almost the same as the famous specimen known as Sioux. The writers suggested that this tooth, along with the older Montana skull bone, showed that Tyrannosaurus might have lived as far back as 77 to 76 million years ago. If true, this would place it right alongside Daspletosaurus, a surprising overlap. Finally, in the year 2025, these same fossils were used as proof to argue that the group known as Tyrannosaurini did not grow directly from Daspletosaurus, showing that the family story of Tyrannosaurus is far more complex than once thought. In the year 2022, the paleontologist Gregory S. Paul, together with his team, put forward a bold new idea that shook the long-held picture of Tyrannosaurus Rex. For over a century, most scientists had believed that all of the famous giant hunters' fossils stood for just one species, the so-called king of the tyrant lizards. But in their detailed study, Paul and his team suggested that what had long been called Tyrannosaurus Rex might in fact be three different species. Alongside the well-known king stood two new rivals for notice: Tyrannosaurus imperator, whose name means tyrant lizard emperor, and Tyrannosaurus regina, the tyrant lizard queen. To support their case, the team pointed to clear differences in the bones of dozens of specimens. The famous fossil known as Sioux, one of the biggest and most complete tyrannosaur skeletons ever found, was chosen as the model or holotype for T. imperator. Another well-known fossil, nicknamed Wankel Rex, was chosen as the holotype for T. regina. The reason behind this split came from the clear variety in the thickness and shape of the leg bones, especially the femur, across different specimens. Some tyrannosaurs had very strong bones, while others looked more slim. The number and setup of small front teeth in the lower jaw, known as incisiform teeth, also gave clues. Based on these signs, Paul and his team suggested a split. The classic T-Rex had a strongly built body, a middle balance between femur length and thickness, and a single slim front tooth in the lower jaw. T. imperator was even more strongly built, with a thicker femur and two of the slim front teeth, and T. regina was the more lightly built of the three, with a longer, slimmer femur and one of the slim teeth. Not all paleontologists agreed with this claim, however. Some of the best-known experts in the field, such as Stephen Broussard, Thomas Carr, Thomas Holtz, David Hone, Jingmai O'Connor and Lindsay Zano, raised strong doubts. Their worries were shared with reporters and later gathered into a technical paper. Both Holtz and Zano admitted that it was possible there had been more than one species of Tyrannosaurus in North America, but they said the proof given by Paul's team was not enough to support making new names. Holtz even said that if T. imperator were truly different from T. rex, it might not need a new name at all, but could instead be the same as another argued species called Nanotyrannus lancensis, which would mean it should be renamed Tyrannosaurus lancensis. Jingmai O'Connor, who works at the Field Museum in Chicago where Sue is shown, said that the proof was too weak to support rewriting the museum's labels. Brusate, Carr and O'Connor all pointed out that the differences named in the study might simply show natural variety within one species, rather than proving the presence of three separate ones. Carr and O'Connor also noted a big problem. Many of the most complete and famous specimens could not be safely placed into any one of the new species. Interestingly, another well-known paleontologist, Philip J. Curry, was first listed as a co-writer on the study but later left, saying that he did not want to be linked with naming new species without stronger proof. Even with the backlash, Gregory Paul did not give up on his idea. In the year 2025, he published another paper defending the presence of T. imperator and T. regina. This time he focused on another feature, the shape of the bony bumps, or knobby parts, behind the eyes of these giant hunters. He argued that these ornaments could serve as another way to tell the species apart. While this debate was going on, another find made the story of tyrannosaurs even more complex. In the year 2024, a team led by Dalman re-examined a fossil first found back in 1983 in the Hall Lake Formation of New Mexico. This fossil, kept at the New Mexico Museum of Natural History and Science under the number NMMNH P3698, included a mix of skull and jaw bones, teeth and parts of the tail. When it was first mentioned in 1984, it was thought to belong to Tyrannosaurus Rex, and by 1986 it was given a fuller write-up. A few years later, in 1990, the paleontologists Lehman and Carpenter suggested that it might really belong to a whole new genus of tyrannosaur. However, in 2000, Carr and Williamson disagreed and argued against this idea. By 2015, Sullivan and Lucas said there was not enough proof to firmly link it to T-Rex, so they carefully listed it only as CF, Tyrannosaurus spirus, and pointed out that it seemed to come from an older time than the classic T-Rex fossils, maybe living before 67 million years ago, alongside the giant long-necked dinosaur Alamosaurus. Dalman and his team, however, went further in their 2024 study. They said that this fossil was a new kind of Tyrannosaurus, which they named Tyrannosaurus macraensis, after the Macrae group of rocks where the bones were found. Unlike T. rex, which lived at the very end of the Cretaceous period, T. macraensis came from slightly older rocks. At first, these rocks were thought to be between 72.7 and 70.9 million years old, but later studies suggested they might be younger, dating to between about 69 and 66 million years ago. This meant that T. macraensis may have lived much closer in time to T. rex than first thought. T. macraensis was thought to have grown to about 12 meters, or 39 feet, long, making it about the same size as a full-grown T. rex. But careful study of its bones showed differences. Its lower jaw was longer and less deep, giving it a weaker bite, and the chin area was less clear. Its teeth were flatter from side to side and duller than those of T. rex. The skull also had small ridges behind the eyes. Interestingly, some parts of its skeleton shared features with other Asian tyrannosaurs, like Tarbosaurus and Zhuchengtyrannus, hinting at possible family links. In the year 2025, paleontologists once again questioned the idea of Tyrannosaurus macraensis as a separate species. A team led by Morrison said the earlier age estimate for this dinosaur was not certain and not as strong as first believed. They pointed out that the fossil of a large titanosaur, possibly related to Alamosaurus, which had been used to help date the Hall Lake Formation, was not a good guide. This was because the rock layers where the titanosaur was found could have formed at very different speeds, making the dating unclear. Morrison's team also explained that the bones of the T. macraensis specimen, the so-called holotype, did not show traits that were truly outside the normal range already seen in Tyrannosaurus Rex. No matter the doubts about its age or identity, the team concluded that Tyrannosaurus most likely started in the landmass of Laramidia, and that its older ancestors may have come into North America from Asia long before it became the top predator. Later in that same year, another team led by Voris went even further. They said that T. macraensis was not a new species at all, but simply another example of T. rex, and should be treated as just another name for it. They agreed that the rock data used to separate it were wrong, and they found that all the supposed special features of T. macreensis were already present within the normal range of T-Rex skeletons. Around this time, Carr carried out his own study on the T-Rex skull holotype and reached the same conclusion, showing that every trait said to prove T. macreensis was also seen in different T-Rex individuals. This was not the first time tyrannosaur bones had caused confusion. In fact, many other fossils found in the same areas as T-Rex were once thought to be from other species. Early paleontologists gave names like Orblicidon and Albertosaurus megagracilis to some of these remains. In the year 1995, the latter was even renamed Dinotyranus megagracilis. But as knowledge grew, scientists later agreed these fossils were just from young T-Rex. There was, however, one interesting exception: a small but almost complete skull found in Montana. This skull, 60 centimeters long, was first described in 1946 by Charles Gilmore, who thought it was a Gorgosaurus. More than 40 years later, in 1988, Robert Baker, Phil Curry, and Michael Williams studied the fossil again while it was in the Cleveland Museum of Natural History. Their work showed the skull bones were fused, meaning the animal had finished growing and was an adult. Because of this, they believed it was a new kind of tyrannosaur, which they named Nanotyrannus, or dwarf tyrant. At the time of its death, the animal was thought to be around 5 meters long. But in 1999, Thomas Carr's detailed study showed it was really the skull of a young T-Rex, not a new species. Many paleontologists agreed, saying Nanotyrannus was just a younger form of T-Rex. In 2001, a more complete young tyrannosaur was found. This fossil, nicknamed Jane, seemed to belong to the same group as the so-called Nanotyrannus. The find led to a big meeting in 2005 at the Burpee Museum of Natural History, where scientists argued strongly over whether Nanotyrannus was real. Many who had once supported the idea, like Curry and Williams, now leaned toward it being only a young T-Rex. But Peter Larson disagreed. He pointed to differences like more teeth in both jaws, larger hands for its size, and differences in the wishbone compared to T-Rex. Larson even suggested that another fossil, known as Stygivinator, often thought to be a young T-Rex, might actually be a young Nanotyrannus. Yet later studies showed that even other tyrannosaurs, like Gorgosaurus, lost teeth as they grew, and the different tooth counts might just reflect natural variation, not proof of a new species. By 2013, Carr said that all of the supposed differences used to argue for Nanotyrannus had been shown to be due to either normal variation, changes with age, or fossil damage. In 2016, a study by Persons and Curry suggested that Nanotyrannus fossils had longer legs than T. Rexon might have been faster runners, but other paleontologists like Manabu Sakamoto warned this conclusion was weak because the sample was too small. That same year, Joshua Schmerge argued that a groove in Jane's lower jaw proved Nanotyrannus was real. But Carr and others quickly pointed out that this feature was not rare and could be explained by growth changes, so it was not strong evidence for a separate species. In 2020, Holly Woodward and her team studied bone growth and found that all Nanotyrannus fossils were really young T-Rex. That same year, Carr published a big paper on the growth of T-Rex. He showed that the skull fit neatly into the growth stages of T-Rex and had the same features seen in other young individuals. His work showed no clear differences in sex or ancestry among more than 40 specimens. Carr explained that what some once thought were signs of a new species were really just natural changes as T-Rex grew from its long-snouted, shallow-skulled youth to its big, deep-skulled adult form. In 2024, Nick Longrich and Evan Sater looked again at the debate. They re-examined the original Nanotyrannus fossils and said that differences in shape, development, and family placement suggested it might have been a separate animal, maybe even outside the main Tyrannosaur family. But in 2025, Voris and his team strongly disagreed, saying Longrich and Saiter's ideas were based on features linked to immaturity and incomplete data. They repeated the now widely accepted view that Nanotyrannus was not a new genus at all, but simply the teenage form of T-Rex. The close study of Tyrannosaurus Rex fossils has given scientists an amazing look at how these huge animals grew, lived, and died. By comparing specimens of different ages and sizes, researchers have been able to trace the life story of this predator, from its fragile youth to its giant adult stage. One of the smallest known Tyrannosaurus fossils is catalogued as LACM 28471, called the Jordan theropod. When alive, this young animal weighed no more than 30 kilograms, or 66 pounds, about the size of a large dog. At the other extreme, one of the biggest adults ever found is Sue, catalogued as FMNH PR 2081. Sue, now displayed at the Field Museum of Natural History in Chicago, was thought to weigh about 5,650 kilograms, or roughly 12,460 pounds, much bigger than the Jordan theropod. By studying the tiny structure of bones, a field called histology, paleontologists learned that the Jordan theropod had been only 2 years old when it died. Sue, on the other hand, lived much longer. At first, scientists thought Sue was about 28 years old, which was close to the longest lifespan of the species. Later research changed this, suggesting Sue was between 27 and 33 years old. Another famous fossil, Trix, labelled RGM 792,000, was also at least 30 years old at death. These findings show that Tyrannosaurus could live longer than once believed. Bone studies of many other fossils helped scientists make what is called a growth curve, a chart showing how body mass changed with age. The growth curve of Tyrannosaurus forms an S shape. For the first 14 years of life, young tyrannosaurs stayed fairly small, weighing under 1,800 kilograms, or 4,000 pounds. Then came a sudden growth spurt. Between ages 14 and 18, they grew very fast, adding about 600 kilograms, or 1,300 pounds each year. By age 18, this rapid growth slowed and the body size leveled out. To give an example, Sue at age 28 weighed only about 600 kilograms more than a Canadian specimen that died at age 22. A study from the year 2004 confirmed this pattern, showing that growth slowed sharply around the age of 16. Later research, published in the year 2011 by Hutchinson and colleagues, agreed with the general pattern, but suggested that the fastest growth rates were even higher than earlier thought. Their math showed that during its quickest growth stage, Tyrannosaurus Rex might have gained nearly 1,790 kilograms in a single year. This amazing rate helped close the gap between measured growth and what would normally be expected of such a huge animal. The slowing of growth at the end of this fast phase is thought to mark the arrival of full physical maturity. One especially important fossil, Moore 1125, better known as B. rex, gave key proof. This specimen, which lived between 16 and 20 years, was found in Montana. Scientists found a special type of tissue in its leg bone called medullary tissue. In living animals, this tissue is found only in female birds when they are laying eggs, meaning B. rex was a female that had reached breeding age. Later studies placed her age at about 18 years when she died. In the year 2016, researchers Mary Higby Schweitzer, Lindsay Zano, and their colleagues confirmed without doubt that the soft tissue in the bone was indeed medullary tissue, proving once and for all that B. rex was female. This find was groundbreaking because it showed that paleontologists could tell the sex of dinosaurs by spotting this unique tissue, something that could help in learning about reproduction in many other extinct animals. More studies showed that while Tyrannosaurus grew at amazing speeds, it was also flexible in how it grew. A study published in the year 2020 by Woodward and colleagues showed that young tyrannosaurs could slow their growth when food was short. By studying 2 young specimens between 13 and 15 years old from the Burpee Museum in Illinois, the scientists found proof that these dinosaurs adjusted to how much food was around. When food was plenty, they grew quickly. When food was little, they slowed down. This skill may have given Tyrannosaurus a special survival edge in changing environments, while other medium-sized predators may have found it hard to survive. The study also reopened the debate about the disputed genus Nanotyrannus, suggesting that it was not a separate species at all, but simply a young Tyrannosaurus Rex. Life for Tyrannosaurus was not only about growth, but also about survival, and the pattern of death among fossils shows a dramatic story. More than half of the known specimens seem to have died within 6 years of reaching sexual maturity. This pattern is not unique. It is also seen in other tyrannosaurs and even in certain large birds and mammals today. Many of these species show a cycle of high baby death rates, lower death rates during youth, and then higher death rates again once breeding begins, as the strain of mating and egg-laying takes its toll. Interestingly, the lack of young Tyrannosaurus fossils might be explained by the fact that they were not dying in large numbers during their teenage years. Because their chances of living were fairly high at that stage, fewer of them became fossilized. Another reason could be that the fossil record is incomplete. or that fossil hunters in the past focused more on finding giant, striking adult skeletons instead of smaller, less eye-catching young ones. In a lecture given in the year 2013, paleontologist Thomas Holtz Jr. famously said that dinosaurs as a whole lived fast and died young. His point was that dinosaurs bred quickly and in big numbers, but rarely lived long lives, unlike mammals which breed more slowly and often live longer. Gregory S. Paul, another well-known researcher, agrees with the idea that Tyrannosaurus Rex lived short lives, but stresses that their deaths were often tied to the risks of their violent lives. These were predators living in a dangerous world, and while they grew quickly and ruled the land, their lives were always at risk from fights, wounds, and the harsh struggle for survival. Through these discoveries, Tyrannosaurus Rex stands out not just as a frightening giant, but as a living creature with a rich life story, one that grew in sudden spurts, bred at a fairly young age, and lived a life of constant struggle in a hard and dangerous prehistoric world. The discovery of feathered dinosaurs opened the door to one of the most exciting debates in paleontology: whether the mighty Tyrannosaurus Rex might also have been covered in feathers, and if so, how much of its body carried them. The story begins in the year 2004, when scientists studying fossils from the early Cretaceous Yixian Formation in China described a small and early tyrannosaur called Dilong paradoxus. This creature, though far smaller than the huge Tyrannosaurus, preserved fine, hair-like structures that were widely taken as the very first step in the rise of feathers. These filaments suggested that the earliest members of the Tyrannosaur family may not have looked fully scaly, but instead may have worn a thin coat of warming plumage. At the time, however, skin marks from larger Tyrannosaur relatives showed clear proof of scales instead of feathers. Because of this, many scientists guessed that while smaller tyrannosaurs needed feathers to keep warm, larger ones like Tyrannosaurus might have lost them. Their great size meant they held heat better, making feathers needless. This idea seemed fair until another discovery changed it. A huge predator named Eutyrannus huali, also found in the Yixian Formation, was shown to have had a body covered in feathers despite its great size. This shocking find cast doubt on the belief that only small tyrannosaurs had feathers, and showed that even giant predators could be at least partly feathered. More proof came in the year 2017, when a study looked at the skin marks of various tyrannosaurids, including a famous Tyrannosaurus specimen nicknamed Y-Rex. The marks from Y-Rex showed a patchwork of small tile-like scales kept on its tail, hips, and neck. From this, researchers decided that if Tyrannosaurus had feathers at all, they were likely limited to certain parts of the body, such as along the back, instead of covering the whole animal. Alongside the feather debate, another puzzle challenged scientists. Did Tyrannosaurus have lips covering its huge teeth, or were they left bare like the teeth of modern crocodiles? In 2016, a team suggested that theropods, including Tyrannosaurus, had lips. Their case was based on the presence of tooth enamel. Enamel, they explained, must stay moist to stay strong, while bare teeth, like those of crocodiles, tend to dry out. This suggested that tyrannosaurs may have had lips to keep their teeth moist. Not everyone agreed, however. A later study in 2017 argued that tyrannosaurs likely had big, flat scales on their snouts instead of lips, much like crocodiles. Yet this idea was doubted since crocodiles do not really have flat scales but cracked, hardened skin. By comparing the bumpy textures on tyrannosaur skulls to the skin of modern lizards, other researchers decided that tyrannosaurs had overlapping scales, something quite different from crocodile skin. In 2023, a new study by Cullen and colleagues reopened the lips debate. They pointed to skull features in tyrannosaurs, such as small holes called foramina, which more closely looked like those of modern lizards and iguanas than crocodiles. They also compared the teeth of the Tyrannosaur Daspletosaurus with those of American alligators. They found that tyrannosaur teeth showed very little wear, while alligator teeth, always bare to the air, were badly worn. This suggested that tyrannosaur teeth had likely been covered by lips, keeping them moist and strong. The researchers also studied the size ratios of skull and tooth in different reptiles, and found that tyrannosaurs did not have teeth so large that they would have needed to stick out of their mouths. This meant that Tyrannosaurus teeth could very well have been hidden behind lips when its mouth was closed. As more Tyrannosaurus fossils were found, scientists noticed another curious pattern. Some skeletons looked more heavily built than others. These two clear forms were called robust and gracile. The robust type was sturdier, with broader hips, while the gracile type was slimmer and more lightly built. For a long time, researchers thought this difference might show sexual dimorphism, that is, differences between males and females. Many suggested that the robust ones were females, as they sometimes had wider hips, possibly to allow room for eggs to pass. Also, some scientists thought that the robust type had shorter bones in the tail to make egg-laying easier, a trait once thought to exist in crocodiles. But in 2005, new studies questioned this idea. The earlier claims about crocodile anatomy were shown to be wrong, raising doubts about the supposed male-female differences in Tyrannosaurus. Proof from Sue, the most famous and robust Tyrannosaurus specimen, showed that she had a full-size tailbone, which went against the earlier idea. Scientists then began to suggest that the difference between robust and gracile individuals might instead show differences in age, or even where they lived. Maybe some areas produced stockier tyrannosaurs while others had more slender ones. Or maybe robust ones were simply older animals that had grown thicker with age. Only one Tyrannosaurus specimen has ever been clearly shown to be female. This is the famous fossil nicknamed B. rex. When paleontologists studied her bones, they found preserved soft tissue deep inside. Within this tissue, they found medullary bone, a special kind of tissue that modern birds grow when making eggs. This tissue gives the extra calcium needed for eggshells, and it only appears in females during egg laying. Because of this, scientists were able to say with certainty that B. rex was a female and that she died while getting ready to lay eggs. This find was hugely important, as it directly linked Tyrannosaurus to modern birds. Crocodiles, considered the closest living relatives of dinosaurs, do not grow medullary tissue, which makes the tie between birds and theropod dinosaurs even stronger. Through feathers, lips, body shapes, and even traces of breeding biology, the mighty Tyrannosaurus keeps surprising scientists. Each new find draws a fuller picture of this ancient predator, showing that it was not simply a scaly, roaring monster, but a living animal with traits that blur the line between reptiles and birds. When Tyrannosaurus Rex was first being studied, people pictured it standing and moving in a way that we now know was very wrong. Like many two-legged dinosaurs, it was once shown as a kind of living tripod, its body held at an angle of about 45 degrees from the ground, with its huge tail dragging behind like a kangaroo's. This old idea went all the way back to the year 1865, when Joseph Leidy made a reconstruction of Hadrosaurus, the first dinosaur ever shown in a two-legged stance. Half a century later, in the year 1915, Henry Fairfield Osborn, who was then the president of the American Museum of Natural History, put this idea proudly on display when he unveiled the very first complete skeleton of Tyrannosaurus Rex. He mounted it in a tall, upright stance, and for 77 long years people believed that this was the true posture of the mighty predator. The skeleton stood this way until the year 1992, when it was finally taken down. By the 1970s, scientists had learned that this pose was completely wrong, and in fact impossible for a living Tyrannosaurus to hold. If the animal had tried to stand straight up like this, the strain would have hurt or even popped out its joints, especially around the hips and where its skull joined the backbone. Still, the dramatic display at the American Museum shaped people's views for decades. Countless books, paintings, and movies showed Tyrannosaurus in this stiff kangaroo-like pose. Rudolf Zallinger's famous mural The Age of Reptiles in Yale University's Peabody Museum is one example. Only in the 1990s, with the release of movies like Jurassic Park, did the public finally see a truer picture. A Tyrannosaurus with its body stretched flat, its head reaching forward, and its long tail stretched out behind it as a counterweight. This low, balanced pose is now the standard in museums, movies, and artwork. But how exactly did this giant sit or get up from the ground? Fossil experts believe that when Tyrannosaurus wanted to rest, it may have leaned back and placed its weight on a special part of its hip bone called the pubic boot, which was a wide part sticking out from the pubic bone. This would let the animal rest while still keeping its back legs free to move. To rise again, it may have used its tiny but strong arms for balance or to push itself up a little. This idea, sometimes called Newman's push-up theory, has been argued about for years, yet most experts agree that Tyrannosaurus could stand up after falling, using its tail and legs to shift its weight back under its middle. Interestingly, some fossils show healed injuries in the arms, which hints they were at least used sometimes, though experts disagree on whether these injuries mean the arms were clumsy and got hurt easily, or whether they show that the arms were active and strong enough to take some damage. When the first skeletons of Tyrannosaurus were being studied, only one bone of the front limb was known, the humerus. Because of this, Osborn, when setting up the grand public display in 1915, guessed that the dinosaur must have had long three-fingered arms like those of Allosaurus. Yet in 1914, the Canadian fossil expert Lawrence Lamb had already described the short, two-fingered arms of Gorgosaurus, a close relative of Tyrannosaurus. This suggested that Tyrannosaurus also had much shorter arms than first thought. Still, the truth was not fully proven until the year 1989, when the first full arms of Tyrannosaurus were found in the fossil of the Wankel Rex. Later, the famous fossil called Sioux also showed full arms. The arms of Tyrannosaurus are tiny compared to its huge body. Each arm is only about 1 meter long, yet the bones are thick and strongly built, with big areas for strong muscles to attach. This means the arms, though short, were not weak. Even back in 1906, Osborn suggested they might have been used during mating, helping the animal hold onto a partner. Others suggested they helped the creature push itself off the ground after resting. More recently, the fossil expert Kevin Padian argued that the arms may not have had a special use at all. Instead, as the skull and jaws of tyrannosaurs grew bigger and stronger through evolution, the arms may have shrunk as a side effect, becoming smaller so they would not get in the way or be bitten during fierce group feeding. Despite their small size, there is proof that the arms were still strong enough to be useful. Their bones are very thick, built to handle great stress, and the muscles were incredibly powerful. The main biceps muscle of a grown Tyrannosaurus could have lifted nearly 200 kilograms on its own, and other muscles like the brachialis would have added even more power. This means that while humans can swing their arms widely, a Tyrannosaurus arm had a much smaller range of motion, only about 40 to 45 degrees at the main joints. However, this limited movement may have made the arms perfect for grabbing and holding struggling prey tightly, while the huge jaws gave the killing bite. Some experts, such as Kenneth Carpenter and Matt Smith, rejected the old idea that Tyrannosaurus had useless arms, and instead believed the arms were made for strength over flexibility. Others, like Stephen Stanley, went further, suggesting that the arms could even have been used as weapons, slashing at prey with their sharp claws to cause deep wounds. But critics like Padian dismissed this idea, saying Stanley's guesses were based on wrong estimates of how big and flexible the arms really were. Even though the puzzle is not fully solved, what is sure is that the short arms of Tyrannosaurus were not the weak, funny stubs that many once thought. They were powerful, specialized tools that played a role, whether in feeding, standing, fighting, or mating, in the life of the most famous hunter ever to walk the earth. For a long time, many people thought that Tyrannosaurus, like most other dinosaurs, was a cold-blooded reptile, much like today's lizards. This meant that its body heat was believed to be controlled mostly by the environment around it. That idea started to change during the time often called the Dinosaur Renaissance, which began in the late 1960s, when experts such as Robert Bakker and John Ostrom argued that dinosaurs were far more active and possibly warm-blooded. Some even suggested that Tyrannosaurus Rex itself may have been warm-blooded, with a fast body system that let it live a very energetic and active life. Since then, many fossil experts have tried to figure out just how this giant hunter managed its body heat. Studies of its bones have shown that young Tyrannosaurus grew at amazingly fast rates, very similar to mammals and birds, which may suggest a high body system. The growth patterns also showed that, much like in mammals and birds, the fastest growth was limited to the younger years of life rather than continuing without end, as seen in many reptiles. Another way experts studied the puzzle was through oxygen isotopes saved in fossil bones. These isotopes can sometimes reveal the heat at which the bone was first formed. In one fossil, bones from different parts of the body showed only a small heat difference, only about 4 to 5 degrees Celsius or 7 to 9 degrees Fahrenheit between the chest and the lower leg. This narrow range led experts Rhys Barrick and William Showers to think that Tyrannosaurus kept a steady inner temperature, something called homeothermy, which is between cold-blooded reptiles and warm-blooded mammals. However, not everyone agreed, because isotopes in fossils may have changed long after the dinosaur died, making it hard to be sure. Barrick and Showers defended their ideas by pointing out that they found similar results in Gigantosaurus, another giant meat-eating dinosaur that lived on a different continent many tens of millions of years earlier. Signs of homeothermy were also seen in other plant-eating dinosaurs, but not in lizards that lived in the same areas, which made the case even stronger. In the year 2022, a new study by Yasmina Wieman and her team used a completely different method. They studied byproducts of cell activity, called lipoxidation signals, that could reveal body system rates. Their results suggested that Tyrannosaurus and many other dinosaurs had body system rates as high as modern birds, and even higher than mammals, meaning that they were truly warm-blooded. This also hinted that such a body system may have been common to all dinosaurs from the very beginning. Even so, the question is not fully settled. Some experts suggest that Tyrannosaurus may have controlled its body heat, not through a bird-like body system, but through gigantothermy, a condition seen in huge animals like sea turtles today, where their large size helps them keep heat. Others have suggested that certain openings in the skull roof of Tyrannosaurus may have helped it control its temperature, just as similar structures do in modern crocodiles. Then came one of the most shocking discoveries of all. In March of the year 2005, fossil expert Mary Schweitzer of North Carolina State University and her team announced that they had found soft tissue inside a fossilized Tyrannosaurus bone from the Hell Creek Formation. The bone, belonging to a fossil called Moore 1125, had been accidentally broken during transport, giving Schweitzer the chance to test it. To her surprise, she found flexible blood vessels, fibrous but stretchy bone tissue, and even shapes that looked like blood cells. These looked strikingly similar to those of modern ostriches. The experts did not know if the material was truly original or saved by some unknown process, but if it was real, it might hold protein traces that could one day help experts guess what Tyrannosaurus DNA may have been like. Since that first find, other tyrannosaurs and even a hadrosaur have been found with similar tissue-like remains, further backing the chance. Tests also showed chemical elements like sulfur, calcium and zinc inside the bones, showing similarities with modern birds, which further strengthened the evolutionary link between them and dinosaurs. More amazing results came in April of the year 2007, when John Asara and his team reported finding pieces of collagen proteins inside cleaned Tyrannosaurus bone. These proteins most closely matched those of chickens, followed by frogs and newts. This was breathtaking because it suggested a direct link between dinosaurs and birds, and it also challenged the long-held belief that all original tissues disappear during fossilization. Around the same time, the team also found similar protein traces in a mastodon bone that was at least 160,000 years old. Many experts praised this as a milestone discovery, saying that fossil study was now entering the field of molecular biology. Not everyone was convinced, though. In 2008, Thomas Kay and his team argued that the supposed blood vessels and cells were not original tissues at all, but bacterial layers that had grown in the spaces of the fossil. They also found tiny iron-bearing spheres, called framboids, and suggested that these were mistaken for blood remains. Schweitzer strongly disagreed with this, saying that bacteria could not have made the hollow branching tubes she saw. Later studies, including a detailed study published in 2011, backed Schweitzer's results, showing that parts of collagen truly had been saved, especially the inner coils that would be expected to last the longest. Other research confirmed the presence of vessel-like branching structures inside fossilized bone, strengthening the case for real soft tissue. For many years, scientists have tried to answer one of the most exciting questions about Tyrannosaurus Rex. How fast could this mighty hunter actually move? The answers have been far from easy, and the range of possible running speeds suggested by different studies is wide. Some guesses place its top speed at about 9 meters per second, which is roughly 32 kilometers per hour, or 20 miles per hour. Others go lower, suggesting a range of about 4.5 to nearly 7 meters per second, which equals between 16 and 24 kilometers per hour, or 10 to 15 miles per hour. A few bold guesses have even gone as high as 20 meters per second, which would be 72 kilometers per hour, or 45 miles per hour, though nearly all experts agree this is very unlikely for such a heavy animal. After all, Tyrannosaurus was not built like a slim runner but more like a living tank, strong, heavy and muscular, so it is hard to think of it matching the speed of lighter, quicker hunters such as Carnotaurus or Giganotosaurus. Because there are no fossilized running tracks of Tyrannosaurus to study, only walking ones, scientists have had to rely on models and comparisons with living animals. In the early 2000s, one report used advanced math and tested its method on living creatures, including alligators, chickens, emus, ostriches, and even humans to guess how much leg muscle a Tyrannosaurus would need to run at high speeds. They concluded that if it were to reach more than 40 kilometers per hour, or 25 miles per hour, its legs would need muscles making up an unbelievable 40 to 86% of its whole body weight. That is simply not possible. Even medium speeds would still need very large leg muscles, and if its muscle weight was lower, the mighty tyrant lizard may have been limited to little more than 18 kilometers per hour, or 11 miles per hour, moving at a fast walking or jogging pace. Even with these limits, Tyrannosaurus did have some special leg changes. Its lower leg bones, the shin, foot and toes, were long compared to the thigh, giving its stride more use. Its foot bones were tightly locked together in a structure known as the arctometatarsus, where the middle bone was squeezed between its neighbours. This smart setup likely helped it move with more ease, passing the forces of each step smoothly up its legs. Later studies gave a more detailed picture. In the year 2020, researchers studied over 70 kinds of theropod dinosaurs, comparing their body size, leg length and ways of moving. They found that small and medium hunters, such as the quick dromaeosaurs, grew long legs to run faster, which helped them both hunt and escape larger hunters. But in giant theropods weighing more than 1,000 kilograms, or 2,200 pounds, speed was limited simply by size. For them, long legs were not about running fast, but about walking farther with less effort. In this way, Tyrannosaurus and its relatives were very good walkers. They could cover long distances without tiring quickly, lowering the amount of food they needed and letting them sneak up on prey with patience. This skill, along with proof that tyrannosaurs were more flexible than other giant hunters, shows they were not sprinters like cheetahs, but rather long-distance stalkers, waiting for the right moment to release a short, deadly burst of speed. Some proof even hints that groups of tyrannosaurs may have hunted together, much like modern wolves, mixing endurance, patience, and teamwork. In the year 2021, another interesting study showed that the tail of Tyrannosaurus played a key role in its walking rhythm. Using a detailed three-dimensional rebuild of a famous fossil named Trix, scientists copied the movement of the ligaments and muscles in the tail. They found that the tail would sway slightly with each step, stretching and releasing like a spring, storing and releasing energy. This natural spring-like action set the dinosaur's usual walking speed at about 1.25 meters per second, or roughly 4.5 kilometers per hour, which is just under 3 miles per hour. This is close to the easy walking pace of humans, ostriches, and even giraffes. Other studies from the year 2017 suggested that the top speed of Tyrannosaurus might have been about 27 kilometers per hour, or 17 miles per hour, though such bursts would have drained its energy quickly. Another study in the same year went further, saying that a full-grown Tyrannosaurus, weighing around 7 tons, could not run at all without breaking its own leg bones if it tried speeds above 18 kilometers per hour, or 11 miles per hour. This would also be true for other giant hunters such as Gigantosaurus, Maposaurus, and Acrocanthosaurus. Yet Tyrannosaurus was not clumsy. In fact, research published in 2019 by Eric Snively and his team showed the opposite, that tyrannosaurs were surprisingly quick for their size. Thanks to their strong leg muscles and fairly low turning weight, the ease with which a body can spin, they may have been able to turn fast, even doing something like a spin on one foot while swinging the other during a chase. This quick turning skill would have been a deadly edge, letting the tyrant lizard king stay close to running prey and outmaneuver rivals. Altogether, these findings show a mixed truth. Tyrannosaurus may not have been the fastest runner among the dinosaurs, but it was a master of balance, skill, and planning. It could walk great distances with ease, save energy, sneak up on prey like a shadow, and then strike with terrifying bursts of strength. Its speed was not in plain kilometers per hour, but in the clever way it used its body. A hunter perfectly built for survival at the very top of its world. In different parts of North America, rare and precious fossilized footprints of giant hunters have been found, leaving behind ghostly marks of Tyrannosaurus in ancient stone. Some of these trackways have been placed in the ichnogenus Tyrannosauropus, a name given to footprints thought to have been made by Tyrannosaurus itself, based on the age of the rocks in which they were kept. The very first of these finds came in the year 1994, when fossil experts Martin Lockley and Adrian Hunt described a single huge footprint unlike any other. Many years later, in the year 2021, another amazing find was shared. This time, a pair of fossil marks showing a massive tyrannosaurid getting up from the ground. The animal had likely pushed itself up using not just the pads of its huge feet, but also its elbows, leaving behind the story of its movements written in stone. These rare fossils were found in Ludlow, Colorado and Cimarron, New Mexico. Even more hints came in the year 2018, when another trackway was found in the Lance Formation of Wyoming. This one may have belonged to a young Tyrannosaurus, or perhaps to the debated genus Nanotyrannus. What made this find even more amazing was that the trackway let scientists guess the walking pace of the animal. The dinosaur seemed to be moving at a speed of roughly 4.5 to 8 kilometers per hour, or about 3 to 5 miles per hour, much quicker than earlier scientists had guessed tyrannosaurids would normally walk. As great as its size and strength were, Tyrannosaurus also had outstanding senses. Research done by Lawrence Whitmer and Ryan Ridgely of Ohio University showed that Tyrannosaurus shared the sharp senses of other members of its group, the Coelurosaurs. It could move its eyes and head with surprising quickness and control. It had a strong ability to pick up very low sounds, vibrations that carried over long distances, letting it track the movements of prey even when far away. Its sense of smell was also very well developed, making it one of the best trackers in the animal world. In a separate study, Kent Stevens studied dinosaur skulls and found that Tyrannosaurus had vision that matched and even beat some of the sharpest-eyed birds alive today. By using a method known as perimetry on rebuilt faces of dinosaurs, he found that Tyrannosaurus had a binocular vision range of 55 degrees, greater than that of a hawk. Stevens guessed that the tyrant lizard king had vision 13 times sharper than a human's, and even sharper than that of an eagle, which is about 3.5 times keener than our eyesight. He said that a Tyrannosaurus could spot an object at the horizon nearly 6 kilometers away, or about 4 miles, compared to just 1.5 kilometers or a single mile for a human viewer. Other experts have explained why such sharp sight was so important. Thomas Holtz Jr. pointed out that Tyrannosaurus had to hunt dangerous prey, ceratopsians like the horned Triceratops, armored giants like Ankylosaurus, and the quick-moving hadrosaurs. These animals were not easy meals, so Tyrannosaurus needed accuracy. It had to strike hard, deliver a crushing blow, and bring its prey down fast. By contrast, hunters such as Acrocanthosaurus, which went after huge but less common sauropods, did not need the same level of depth vision. Even though no full eye ring has ever been found for Tyrannosaurus, Kenneth Carpenter guessed its likely size based on close relatives like Gorgosaurus. For the famous fossil known as Stan, he calculated that the ring would have measured about 7 centimeters across, with an inside opening of 3.5 centimeters. This pointed to a pupil about 2.5 centimeters wide and an eyeball nearly 12 centimeters across, close to the size of a grapefruit. Such numbers let him guess the eye's ability to take in light. His view was that Tyrannosaurus probably did not see well in the dark. Its eyes were better for daytime sight, meaning it hunted mostly in the daylight hours.